have a sense of, okay, maybe method C is better than A, better than D, better than B, better than E. The way we're able to do this because you can evaluate on your test set. You can clearly see how well your model is doing on your benchmark. Now, I think having this sort of ranking gives you two advantages. The first one is that we know what is the state of the art in the field. We know what is the actual best method if you want to do a detection, right? And the second one is that if you're a researcher and you're trying to create new algorithms, you know where to start. You know which algorithms to start off and try to build on top of. But unfortunately, we don't have this in robotics, right? Many times we don't know what's the state of the art in the field. And then as a researcher, it's often hard to say what is the right place to start from. So why is this the case? Why can't we just easily run this same strategy in robotics? Okay, I think there are three reasons for this. The first one is that it's very unclear what should you try out first. In computer vision, you can just go online and there's already pre-written algorithms to try out first, right? And then based on what you have seen in prior work, past papers, you just choose a bunch of them and try them out. But in robotics, if I look at the spectrum of algorithms here, very rarely can you go online and just download something and try it out on your robot. Oftentimes, trying out even any one of this is a huge hassle, even for an expert, right? So clearly, this is not easy. It's not easy to say what methods I should try out first. Next, after I have a bunch of initial methods to try out, how do we actually rank different methods? In vision, it's quite easy. We have a fixed benchmark. We try out all the methods on the benchmark, and we get a ranking. But in robotics, maybe method C was tried out in one lab, method A was tried out in a different lab, and now there's no way to compare the absolute results, right? Because if two different papers are using two different environments and two different robotic systems, how will you actually compare the numbers from those two methods? So this is our second issue. Now, one way of trying to solve this issue is just to make sure that everyone uses the same setup, right? Everyone uses the same robot, same environment, same objects, everything is the same. But then we hit the third issue, that is, where do we benchmark, right? What is this one same setup that everyone has to use? Again, in vision, it's quite easy. There is a consensus in the community of what sorts of data sets need to be used. But in robotics, there's no consensus. Everyone just uses their own environments, their own objects, own robots. And so there's no way in which we can get an agreement, right? At least for now. Okay, so in this talk, I'll try to give some perspectives and answers to a few of these questions. Of course, almost everything I'm saying here, you should take it with a grain of salt because a lot of it is a personal opinion. And then at the end, we can sort of have a discussion of where we can go forward in the future. Okay, so let's start with the first question. If I have a problem, what is the first robot algorithm I should try? Right? How do we figure this out? Now, in the famous words of Dwight Schrute from The Office, we want to keep these methods as simple as possible, right? You want to choose algorithms and starting frameworks that are as simple to run as possible, right? So with that kind of thought, what's the simplest robot algorithm to try out? Well, I think it is imitation learning. And there's a few reasons for this. But I think one of the sort of intuitive ways to think about it is this is actually how humans learn fast. This is the easiest way for humans to learn. If you want to solve a problem, you see someone else trying to solve it, and that's how you solve that problem. A nice example of this is the high jump. So I'm not sure if all of you are familiar with this, but if you were doing high jump prior to the 1960s, the way you would do it is either by doing a scissor jump or a straddle jump. As you can see, it doesn't look very elegant over here. And then in the 1960s, I think in the Mexico Olympics, there was this guy, Mr. Fosbury, and he invented this thing called the Fosbury flop. Now, the reason this is really cool is because he figured out a way to jump over a certain height while keeping his center of mass under that height, right? Because you can see his legs are underneath the pole as he's jumping over it. Okay, so after he did this, almost overnight, all the athletes over here tried to switch. They switched into using this Fosbury flop. And if you look at high jump nowadays, almost everyone is doing a variation of this, right? Now, clearly, this is not an easy strategy to just stumble upon because it took years and years until one person had figured it out. But after one person found it out, it's very easy to imitate that one strategy. Okay, so let's try to use this on robots. Let me try to convince you that this is actually very easy to get started with. So here are a few examples. So in this work, what we do is we use a reacher grabber stick, which has a camera on it, to show a demonstration of how to open doors. And then we want to transfer this behavior onto a robot. So we just collect a few demonstrations, maybe around 20 to 30 of them, and then run a very simple algorithm. You just take images that were seen, feed it into an encoder, you get a representation which is small. And then from these representations, you do the most stupidly simple thing, which is nearest neighbors. Just do nearest neighbor matching in order to get actions. And just by this strategy, we're actually able to train robots. So over here, it shows like a single run. So let's say your robot is in that position. It sees an image on the top right. Then from that image, it finds its nearest neighbor matches. Again, no, they don't have to be exactly the same. It can be a different viewpoint, different lighting, and so on. And after it sees the actions, you aggregate all those nearest neighbor actions, and then apply this action on the robot. After it applies the action, it sees the next image, right? And then keeps doing the same process over and over again. So here is a video of it running. And in the inset video, you can see what the actual observations of the robots are. And the action is shown in the red arrow. So one of the nice things about having a simple algorithm is if you now want to extend it to any other door, let's say over here, I just need to collect a few demonstrations of this door and ask the robot to then solve it. And the same algorithm almost immediately works on this door as well. Okay, so we also compare with a bunch of prior work and actually see that, in fact, having a simple algorithm works a lot better than having end-to-end training and using pre-trained representations and so on. Okay, if you're interested in this, all of our code and our data is online. So feel free to have a look at this link. So this is actually a quite simple task, right? If you think about opening a door, it seems like a quite simple task. You can easily do this with 2 fingers. But what if I want to solve a harder task? Let's say I want to solve a task in dexterous manipulation. So over here, let's say you have a robot hand with few like 4 fingers on it, and I want to do some sort of in-hand manipulation with this robot. So if I was going through the approach of imitation learning, I need to start with a few demonstrations. Now, if I use a cyber glove, this is way too expensive and requires calibration. It's definitely not simple. Another approach is to create a system of cameras around the scene to sort of see human hands. And then once you are able to understand human hands, you can then teleoperate the robot using this hand. But again, over here, because you have a system of cameras, you require calibration. So how can we make this even simpler? Well, instead of a system of cameras, why don't we just use only a single camera? So this is what images of a hand will look like from a single camera. And if you can use this sort of framework, it's going to be cheap and you don't need calibration, or you need very little calibration. Now, this idea has also been explored in other works in this year. And over here, I show you an example of how this works. So on the left, it's a human moving the hand. And on the right, it's a robot trying to copy exactly what the human is doing. The way it works behind the scene is we use standard computer vision algorithms to get a pose detection of the human hand and then transfer this pose onto the robot. Now, if you want to solve a task, let's say I want to do some sort of cube rotation, I just drop the cube onto the hand and ask the human to figure out how to move this cube inside the hand, right? Now, if I actually want to train a policy for it, I need a bunch of these demonstrations. And since each of this, it only takes a few minutes to collect, I can just ask this human to give me a few of these demonstrations. So in total, for this specific task, we use around 30 demonstrations. So all that you're seeing here is all the demonstrations seen by the robot. And with this, to train it, we again use the most simplest approach, just nearest neighbors. And with just that and those 30 demonstrations, we're able to run a robot policy of this sort. So note that once the object goes offhand, it will actually start using the other fingers to bring it back onto the palm. And this is all automatically learned from the demonstrations. Okay, so again, this is just simple imitation learning, and it seems to work quite well on a bunch of different sorts of problems. Again, if you're interested in this, our code and our data is all online. Okay, so to answer the first question, what sort of methods I should try first? My opinion is that you should try some sort of imitation learning algorithm, because A, it's easy, and B, you can very easily see in what cases it's failing and what cases it's not. But now let's go to a second question, right? How do you rank different methods? To motivate this, let's say you were trying to solve a task and you're just trying to read through like a bunch of RL or like a robotics papers to see what is the state of the art in the field. But if you look at every published paper, they all create a new algorithm and say that their algorithm is the best algorithm, right? And if that is indeed true, then we have like a cyclic thing where like A is better than B, B is better than C, but C is also like better than A, right? So you have like a cycle over here. And the reason we have this is because every time people evaluate, they evaluate on a different environment. And if you're evaluating on a different environment, the absolute numbers, they don't make sense anymore, right? Another issue with this is that this sort of evaluation mode often favors large labs, because large labs have inside knowledge of what works where. And this inside knowledge, it doesn't come across in the papers. So how do we solve this? Well, the most straightforward answer is to do good benchmarking. And if you can do good benchmarking, there are two advantages. The first one is that it will be useful not just for your lab, for your research, but it will be applicable to a wide range of audience. Right? The same benchmark, it can be used over and over by other labs as well. And the second one is that your experiments and the results of your work will be, in a way, also reproducible, because it's the same framework, right? If it's the same benchmark, those numbers will be comparable across all sorts of papers. But this is not, so this is easy to do in computer vision, where you have a static data set and just evaluate on it. But for a robotics problem, this is not easy at all, right? As all of us are familiar, if you have tried to run a robot experiment, it is very hard to recreate the same experiment like over and over again. Now, this becomes even hard if you're trying to expect two labs to create the same framework. Oftentimes, if you look at lab A and lab E, the environments they'll have are completely different. And because they are not the same, the absolute numbers of running various algorithms is not going to be the same. So how do we fix this? Well, the way to fix it is we have to view benchmarking in a slightly different way when it comes to running things on the robot. So what we have seen is that if you're trying to create the same setup in every lab, that is hard. But instead, what we see is that the relative rankings between various approaches are usually the same, right? So if I'm in lab A and I try out 4 algorithms, the ranking of those 4 are usually the same if I try out the same 4 baselines in a different lab. And so if this is actually the case, what I can then do is take these robust local rankings and combine them into a single global ranking, right? So what's happening over here effectively is you're not taking the absolute numbers of them, but you're going to now start using the rankings of them. Okay, so let's see this in action. Let's say there's a new lab, let's say lab C, and they want to solve the task, right? So let's say you're a new researcher, you have just started a new lab, and you now want to become a part of this new benchmark. So the way you'll do it is you'll first go on to our platform, which is called RB2, and you'll see what the global rankings are for a bunch of different algorithms, right? You will then recreate the best baselines from RB2 on your framework and see what the local rankings are for those algorithms, right? You don't have to try out all the baselines, only try out, let's say, the best 3. And you can see over here, you have a local ranking of that. Now, after this, try out your own algorithm, create your new robotic algorithm and try it out on your environment, right? So here, if you note that your environment is staying the same across all these rankings. So now you have a local ranking of your method across a bunch of previously test baselines. Once you have this local ranking, you contribute it back into RB2. So now when you send it back into RB2, we will collect these local rankings and then rearrange what our global rankings are. Okay, so let's say you had a method and it works well in your environment, but it doesn't work well in a different environment. What happens then? Well, a new lab which has to recreate a baseline will try a method. It will not work well, and then your global ranking will come down. Okay, so right now we have a set of 4 manipulation tasks in RB2. The framework over here is again in terms of imitation learning. So you'll have to collect a few demonstrations, train imitation learning algorithms on it, and then compete for rankings with those imitation learning benchmark numbers. If you want more information about what sort of object sets, how you collect data, what is the metric, feel free to go on to rb2.info for more information. Okay, so we have already started running a few experiments over here, and here is what we have seen so far. So we have tried out a bunch of algorithms all the way from open loop behavior cloning to offline RL. And we actually found some very surprising results, right? So I think the most interesting thing is that just straightforward open loop behavior cloning actually wins on almost all the benchmarks we tried it on. And so it really shows that learning closed loop controllers in imitation is actually quite hard, right? Now, if you think that we're wrong, well, submit your algorithm. You can go online, upload, run our benchmark on your environment, and try to change these rankings over here. Okay, so this work was a collaboration with a bunch of people from Carnegie Mellon, NYU, WPI, UIUC, and FAIR. And hopefully we'll keep expanding this and have more benchmarks and more environments into RB2. Okay, so last, I want to go over where should we actually benchmark. So in any cases, we don't want to compare across labs. We just want a single benchmark where we all can say that, okay, this is the absolute best algorithm, and this is the absolute best number on these tasks. So one of the issues over here is that when you're creating a benchmark, there's a lot of nitty-gritty involved, right? What robot should you use? What algorithms should you try out? And then what sort of objects and data sets should you collect on your robot? In computer vision, we have standardized this, right? For the equipment, just use a bunch of GPUs. For your algorithm, just go to PyTorch and you'll find something over there. And then for your data sets, you just go and download ImageNet, right? So it's quite easy over here. In robotics, this is not easy at all, right? So how do we standardize evaluation over here? Now, I think the only way to create the same benchmark that everyone can use is that we actually have one single benchmark that is on a cloud. And then every time you want to evaluate a method, you send your method to this benchmark on the cloud, right? So let's say you're a researcher, you have a clever idea of how to solve a problem, you code it up, upload it. We on the cloud will run your method and see how it works. Now, since this is a single benchmark where it's like one environment, you can actually get absolute numbers and absolute benchmarking understanding of your method versus every other method. Now, as you keep also interacting with this, all the data we create will also be open sourced, right? So as more and more people use this data set, we'll have, or use this benchmark, we'll have more and more experience and data, which can help improve the field as we keep using it. Now, I think another important aspect of this is we can actually start democratizing in robotics. Instead of a few large labs, pushing a lot of the research, even a researcher who just has a laptop can now start creating algorithms and getting real robot numbers. And once you have these real numbers on a robot, we can have it in every single learning paper. I think another important aspect over here is that once we have a standardized benchmark, all sorts of ideas will have an equal footing, right? Because it doesn't matter if this idea is from a large lab or from like a high schooler. As long as you get improved numbers on the benchmark, it is a valuable idea. Okay, so there are many open questions over here. For instance, what sorts of hardware should we use in this cloud robot? What sorts of examples of tasks should we have over here? How much access should we give the user into this benchmark? Now, we want your input over here. And if you do have ideas, please feel free to reach out to us. So Victoria over here is leading a lot of this effort. And so her email is here. So if you have questions and ideas of how to contribute and add onto this robot cloud, please feel free to reach out to her. So with that, I will end this talk. I do not know if we have a lot of time for questions.
Yeah.
Okay, yeah, so there's some time for questions, but I will end over here. Yes.
So, hello. All right. I worry that there's a fundamental problem with I don't know, trust and ability to implement some of these complex systems. Right. One of the reasons I download the latest computer vision algorithm.
Mm-hmm.
I'm sure we've all tried this out, right? We can apply it to the standard data set and we can get pretty close to those results.
Yeah.
But, we apply it to a new data set and it looks nothing like what we expect, right? And that's because we're not the experts. We don't know how to tune it. We don't know how to make it exactly the way it's supposed to be. Now you're taking, on a lot of this, you're saying, okay, we're going to apply it to this system. We're not experts at that algorithm, right? How can we trust that the results that we got out of it are the same results that the experts would have gotten out of their system?
I think this is a great question, right? I think there's multiple levels to making an algorithm work, right? But I think the first level is to at least make it work on, at least make it in a way on the same benchmark. I think we're not even there in robotics yet, right? Like if I give the same benchmark, it's hard to even get the same number on that benchmark. And I think only after that, we can try to see, okay, for a new benchmark or a new sort of problem, how do these algorithms transfer there? So I do think it's a important problem when we take non-experts trying to try out expert methods on new sorts of problems. But I think what we're trying to do is just like start from somewhere, and we start from making it comparable on the same problem. Right? Yes.
Yeah, thanks for the talk. I kind of another question in a similar direction for the relative ranking. So what it sounds like is that if one person finds a relative ranking that has method A be better than B, but 10 other people find that B is better than A, the global ranking will show B is better than A.
Yeah.
So it seems this is pretty vulnerable to someone just spamming, right? Like someone could just upload a bunch of things that drive their average up or down.
Yeah, I think this is again a great question, and in fact, something that a reviewer had also mentioned, that what happens if there's a bad actor. And I think for a lot of these sorts of problems, right, we are trying to rely on in some sense the good faith of the community.
Yeah.
Now, of course, there are in order to prevent the occasional bad actor, we will have a researcher who's also involved in this process. And so if they see, oh wait, there's this random algorithm that is super high on the ranking, let me actually try it out and see if it's actually true. Okay. So I think that is one way in order to stop a bad actor. Another way to stop it is to actually have an absolute ranking, like having the cloud robot.
Yeah.
Right? So yeah.
Yeah, thanks for the talk. So I have a question about for the cloud robotics. People, I think in the past work, they also have different focus for each project. Like for example, one project might emphasis on what can we get out of play data or random data, while others have perfect demonstrations or experts. So in the cloud robotics, how do you think we can take into account those axes? And also maybe for example, the training time or what it takes to train the model varies largely between models. So I'm not sure. What do you think for these axes?
Yeah, I think this is again a great question, right? Because it's in a sense asking, what is the framework you want to start from, right? What is the sort of ecosystem of algorithm that you want to start from? In a lot of these methods, we do imitation learning, right? So it's you either have to collect a few of these demonstrations, or we will collect a few of these and give it to you, right? And so I think we have to make a choice. There's always a pro and con of each approach, right? There are many realistic problems for which getting a demonstration is actually not a feasible option, right? But we have to start from somewhere, right? And so I think So there are a lot of these pros and cons, but we have to choose one of them and just like power ahead, at least on that one problem. And I think another aspect is that we need some sort of community involvement as well. It's very hard for one person to be like, here's a benchmark, right? The way a benchmark works is it's a community effort where like everyone shares their ideas, and from that we're able to find which is the best way to go about it. Yeah, so just answering your question, the way to solve it is that everyone should reach out to us and say, okay, this is what we want in the robot cloud, and then we can aggregate all of that and sort of have that as a benchmark. Yeah.
Thank you, Laurel. You'll have more opportunity to ask some questions later when he's on the panel in the afternoon, but let's move on to our next speaker. So our next speaker is Bert Crowley, and Bert is an assistant professor at WPI. His research primarily focuses on robotic manipulation, and he's specifically interested in developing multimodal robotic policies that use visual signals to adapt to uncertain environments. And he also wants to apply his research by building robots that are useful for sustainability projects.
So do I share my screen?
This is on. The better.
Yeah. Okay. Cool. And then share my screen. Nice. Wonderful. Okay. Let me also have some timer. Wonderful. Hello, everyone. Great to be here. Thanks a lot for the invite. So I will mostly talk about benchmarking and competitions for robotic manipulation. So it will be more focused on that, but I will also talk about some like methodology of how we try to drive, or more like encourage the community to drive benchmarks. So my presentation will have, it works. Yes, 3 main parts. So the first one will be about benchmarking, but again, I will put it like I will focus on the process that we went through in order for encouraging benchmarking in community, rather than specific data set or whatnot. Then competitions. What are the available competitions? There are, I mean, of course, definitely not a complete list, but some of them. And then if we have some time, a new data set and a competition that we have on recycling, robot waste sorting, actually. So first of all, if we start with benchmarking, I will mostly be focusing on a timeline on YCB data set and the stages that we went through. And basically, so YCB benchmark, like object and model set, it's a data set that we can use for benchmarking. It was a benchmarking tool. But I just want to say that it was just one aspect of this work. There were also connecting researchers together and creating common venues in order to encourage people to benchmark. Actually, I will take very much where you left off in terms of like creating that community, like how important it is. It's been mostly focusing on that. And that's, this is the timeline So we started this project in 2014. And then what we did, first of all, is that it mostly stemmed from this frustration from us, like most of us. So these are actually the reviews that I got maybe more than 10 years ago now. And the reviewer was very rightfully complaining about you do not compare your methods with each other. We don't even know what their performance is. Like you choose your own experimental setup. I was like, okay, but everyone else is doing the same thing. No one is comparing about anything. No one is like, also, especially back then, but even now, I see very little comparison between algorithms. Sometimes people compare within their own algorithms, like how much they improve, but not much with anyone else. And back then, especially, like this was some of the objects that people were picking and choosing. Again, like what else we would do, you choose your own sets and then go and have your own experimental procedures. So instead we said, okay, can we at least maybe have some standardized objects that we at least start standardizing the experimental setups, maybe. And then this is what this is the crew that we started in the first place. Then it grew. So Google added some high quality data. I moved to WPI. UMass Lowell, a big shout out because they have been distributing the set since 2018 in a very robust manner. So what happened is that we basically looked into the objects that are used in the literature. We looked at the objects that are used in rehabilitation fields. Also, we looked at the tasks that robotics community are aiming, and then had some additional constraints like variety, use, durability, cost, portability, etc. In the end, we put together the set and high quality 3D models of them. And now, how do we distribute this? We had a workshop in ICRA and we announced it and said, if you pre-register, you will get a object set. And we distributed like 25 object set during that conference. We literally like carried these like 25 of these huge boxes and just hand them in to the researchers there and said, good luck moving this back to your lab. So we distributed the first 25 sets like that and started selling the rest online to what it costs. And again, UMass Lowell have been doing a very great job setting up a robust process, still continues to date. We distributed around 2,250 sets all around the world. And we started seeing these objects appearing in research papers and everything. It was great, but of course, it's just now people are using these objects. They are still choosing the ones that they want. They are still using the experimental procedures that they come up with. So can we, like, we cannot really compare things yet, right? So what we did then was that another workshop, 2017 IROS, and this was about connecting researchers together. We made 8 groups from various subfields and various different institutions. So we reach out to them. Basically, we came up with this kind of, so this is 3 of those groups, those working groups back then. As you see, many different institutions. Actually, most of these researchers never collaborated with each other before, but they are working on the same topic. Can we then, so with this kind of approach, we are hoping to reduce overfitting, improve the dissemination of the benchmark too, because if, let's say, 3 research groups are designing this benchmark, at least we have 3 algorithms implemented on the same benchmark, right? And you cannot really design the rules of this benchmark to your specific algorithm. Instead, you design something that would work for at least for all these 3 groups. So it has a larger base. And foster collaboration. So in this workshop, they had some community feedback. Good. Then you're like, nice, but nothing works without papers in academy, right? So we need some award mechanism. And a concrete timeline. We can discuss things forever. Like, especially something like a benchmarking thing. I have been in work groups that lasted like 1.5 years, and we still couldn't decide on the metrics and everything concretely, okay? With a timeline and with tighter collaboration with the benchmark and community feedback coming from workshops, we're like, okay, what can this go somewhere? The thing is that we had a array letters spatial issue, not only for people who have been participating in the workshops, but of course it's open to everyone. So we also had a letter of intent mechanism for this array letter spatial issue on robotic benchmarking for robotic manipulation. We received 25 letters. Then we were like, okay, we received 2 letters, for example, for in-hand manipulation. In-hand manipulation community is not that big, or it is growing now, but it was like even a couple of years ago, not a lot of people working on in-hand manipulation. So we're like, hey, do you want to work together? In a kind of like double-blind way, like telling that, hey, there's another group also wants to work on this. Do you want to collaborate with them? All of them said yes. So we had 3 of these cases. We basically connected people working on different topics. Same topics, but wanted to propose benchmarks. Then another workshop. This time, they were actually preparing the drafts of their papers. And in this workshop, so for the people who submitted letters of intent, we were like, okay, now come. And again, feedback from community. Eventually, the spatial issue has been published. If you want if you want to check a summary of all the papers, this is like the guest editorial paper that summarizes everything. But it has like deformable object manipulation benchmark, robotic hand benchmark, grasping benchmark, in-hand manipulation, aerial manipulation. There are 14 benchmark papers there. Some of these look into mechanisms, like benchmarking mechanisms like robotic hands. Some of them are about grasping. So this is more like algorithm level. This is the in-hand manipulation paper that has been in collaboration with Utah and KTH, for example. Those were the 2 collaborating groups, as far as I remember, if not more. Probably there was more there too, but system level benchmark, some system level benchmarks. Now this is a little bit like benchmarking an end-to-end process, more like so we basically converted a box and blocks test, which is a rehabilitation test, into a benchmark. So again, this was a path that we followed just to encourage the community. Except for the box and blocks, none of these are my work, of course. Like I'm just presenting other people's, like just letting you know about other people's work. The thing is that now we have benchmarks like that went through a process, right? Of course, add to this peer review, right? There has been peer review of the journal, of course, editorial review, etc., etc. Of course, like there could be other ways of encouraging the best benchmark, but also now we have this benchmark. Who uses them? I don't know yet. They are relatively new, and I don't think many people know about them. So now I am in the stage 4 or something, telling people that, hey, there are benchmarks. So it is a very it's a process. It takes a lot of years, or like in this case, it did. Maybe there of course there could be much more efficient ways of doing this, and maybe we can discuss all together what we could have done all together to make these benchmarks, like encourage benchmarking for manipulation, or design these benchmarks with a community effort. The second part, do you have any questions up until now? Okay. Competitions. So I will mainly be focusing on robotic grasping and manipulation competition that has been happening in IROS and ICRA. And organizers, list of organizers here. So next one will be happening IROS 2022. Please participate. So this will be happening in hybrid mode. You can either join it from your lab, or you can move your setup to the conference venue. There are three main tracks. One is service track, manufacturing track, cloud manipulation track. Let me talk about them a little bit. So this is a service track example from IROS 2020. In this case, the attendees are asked to make matcha tea. So they are picking cups from a stacked pile. They pour some water. They put some matcha powder with a spoon to the cup, etc., etc. What we do here is that, so they were participating 2020 from their labs, right? So what we did was actually, let me show that parts. These are all videos from YouTube, by the way. Like if you go for robotic grasping and manipulation challenge, you will see many of these videos. So we were setting up 3 cameras, not we, they are, but we wanted them to stream them to us. So we are the judges, right? So there are, of course, all this like how these are pointed, like how they are scored. They're all quite clear in advance. And we basically ask them, so we want them to repeat this process multiple times and move the objects around between, between cycles, so that it is not something that is pre-programmed or anything. This is ICRA 2022, which was like, this is what IROS 2022 will also look like, more or less. It's like a table setup task. You see here one of the groups solving this task. It will not be exactly this, but it will be similar to this. You still have a lot of time if you want to participate. There are, so you set up the table, you set up glasses, you pour some water to these glasses. There's a container of ice cubes. They are like plastic ice cubes, but still. So you pick up a tongue and then pick up an ice, put couple ice to a glass, etc., etc. So this is a solution that they came up with. The other thing is, the other track is manufacturing track. In this case, you have a board that you assemble and disassemble this board. This board is distributed for free to the attendees. This is a NIST task board. And so you will have this shipped to your lab in advance if you are participating in the manufacturing track. This is very new. So this is cloth object set. Cloth manipulation track, which will be mostly about folding and unfolding cloth items. Again, this is a very new track. But if you participate in this track, again, you will have a cloth object set shipped to your lab. If you are interested in cloth manipulation research, this is something that can be used as a standard set that we are hoping to distribute widely. Okay, so this is a completely cloud-based method. So this has been actually sponsored by Alibaba. It went through 2 years. I guess it happened in 2020, happened in 2021. So they put it on hold for now, for this year, but maybe happening later. So you basically, you get it's a pick and place task. You get a desired configuration of these objects. and it's a cluttered scene, and you try to like pick place, and then try to make up that scene, basically. So you upload your solution. So how this worked was, probably this is very relevant to this workshop, right? How this worked was that they actually there was a simulation pre-qualification phase. You submit your solution, they run through a simulation, and then if you pass that phase, you have access to real robots. Now, you can reserve some time slots with the real robot. You upload your solution, they run your solution, you see what is happening, and you iterate, and they have actually a list like of the competitors, like the leaders board, that is getting updated frequently. So they don't, but they give some awards, for example, money awards or whatnot, during conference times, like IROS, ICRA, etc. So there are some deadlines with regards to that. So this was also happening from robotic grasping and manipulation challenge framework. But again, this part is discontinued for now, but the other three, the service track, manufacturing track, and cloud track, will be happening. Any questions for now? All clear? Okay. The last part of my presentation. So this is about a new data set that we put through for recycling robots. So our lab is manipulation and environmental robotics lab. So what we are doing is we try to identify environmental problems that robots can help solve, and try to identify the manipulation problems therein and provide some solutions to them. And this particular project about waste recycling, and this is how much waste that we have been producing, and a forecast of it through 2050. So this is metric tons of waste per year. Sorry, million tons. So there is an increasing trend all around the world for the waste that we are creating. So basically, in 2016, the world generated 1.8 billion tons. In 2013, sorry, and in 2016 it was already 2 billion tons. So there is an increasing trend. And in the United States, we recycle around 32% of the waste. When it comes to something like plastics, it's below 10%. Metals are a little bit easier, so they come close to 50%. Yeah, single stream recycling, which means that everything gets collected to waste sorting facilities. This is what a waste sorting facility looks like. So the impossible job here is to, of course, get every single thing according to their material type, right? This is perfect for robots, right? But this is exactly the amount of clutter we always deal with in our laboratories. Yeah, it is really a very interesting problem. So this is actually a part of this work is manual, a part of this work is mechanized already, and it is it's a very complex domain. Let me tell you that only without going into detail. The economics of it, the worker implications, it changes from region to region too. A waste sorting facility in New York City versus a waste sorting facility in Vermont will look completely different, right? Both size, waste characteristic, what people consume. In Vermont, for example, we have seen a lot of deliveries from pet shops, because there are a lot of home pets, and people just like deliveries. So there are a lot of cardboards like that. just a very quick, little example that you can just scale it as much as you want. And so this is a setup that our undergraduates put together actually. So there's a weight recognition system together with, so what this does is it sorts only cardboards from a running waste stream. This is ×2. And lets everything else through. So it only focuses on the cardboards, basically. Well, so as you see, there's a waste recognition aspect of this. So this, what we did is we went to these facilities, we collected data. We collected data both from the beginning and end of this process. So the beginning one is more like a mixed waste, and the end one, after sorting, is more or less sorted version of this. So we have an example with positive and negative, and another example with mostly negative. So we actually made a data set out of this. So this is the first data set that is collected from actually operating waste sorting facility, labeled with segmentation masks as well. So and the type of each material. And there's a competition. Registration starts today. No, not today. I think it was it 1 month ago? Maybe it was 1 month ago. But I think it was July 1st, but maybe I'm mistaken. So what is happening here is that we also have some synthetic data with an artificial conveyor belt and whatnot, real data, and another real data that are collected from 2 different facilities. So can we basically have a domain adaptation method that can combine these properties, or that can solve this problem basically, and make an algorithm that can adapt to this new domain? Is the scope of the challenge. Here are the organizers, and this is called Vista Challenge 2022. If you are interested. Another thing that I want to very quickly mention, again, we are focusing on environmental applications. So if you, again, our undergraduate students put together an excellent website about environmental problems, some environmental robotic solutions, so environmental-robotics.com. And they also explain some environmental frameworks. This planetary boundary is actually a great framework in the sense that they say, here's the environmental problem, here's where we are at, here's the critical threshold that we shouldn't exceed. Therefore, here's the urgency of this problem, here are some expected solutions. Yeah. But there are also, of course, like some robotics applications, grants, competitions, companies, academic research, etc. So long story short, I think I just put it here as a part, maybe saying that maybe everything has different roles. So benchmarks, for example, is a self-assessment procedure. You would expect to have novel solutions as platform dependent. Whereas competitions, it's more like assessment via a judge, right? And novel solutions are not usually expected. It's more like let's put together what we have in the best way possible kind of framework. And it's platform dependent too. Whereas cloud ones are automated or judge based one. Novel solutions are expected, and is platform independent. Yeah, I think that's the end of my presentation. Do you have any questions? Thank you. Yes.
So competitions are a really good way, I think, of creating benchmarks, right? And so my question I have for all these competitions you talked about is how do the judges judge these things? Is there evaluation metrics, or is it more of, I mean, anything I've ever judged robotics based has been human biased very much, right? It's just that one looked the best and worked really well consistently. So yeah, let's give it to them kind of thing.
Yeah, I mean, for example, I think I can only go with examples. When you prepare matcha tea, for example, picking up a cup and placing it, picking up is like 10 points. Placing it properly without dropping it, 10 points. And like so the more you proceed, you get these points. Like you basically pick up a spoon, you get the matcha tea. If you pour some matcha tea to the table, then you lose some points. So they actually shake it a little bit before they put it. And so there are some clear rules. Is there human bias? Of course, like any of these, right? But anything else? Yeah.
So I have a question about the ICB data set.
Yeah.
So I see that a lot of people use the object sets, but not really use the actual benchmarks. But that's very sort of like if you look at other fields, like almost every work has a predefined benchmark in that work.
Uh-huh.
But even though people are using ICB objects, why don't they use the benchmark as much as they use the object?
The benchmarks that we had in the paper and like on the websites, the first ones on the website, they were really just some examples, and like we tried to put together some templates, etc. The benchmarks that people developed, like in this letters, I guess most of them are using ICB objects too, and they have concrete benchmarks.
I see.
So, and this is a more of a community effort, right? The other is like something that we like put together. Who cares about what we think, right? Yeah.
Thank you.
Great. I think we should thank our speaker. Next up, we have Colleen Devon. Colleen is a research scientist at DeepMind, and prior to DeepMind, she received her PhD from UC Berkeley in computer science. Her research lies at the intersection of deep learning, computer vision, and robotics,
So much.
with a specific focus on transfer learning and representation learning. Her recent work has focused on developing efficient RL algorithms that can transfer to new teams and environments, as well as representing incorporating objects into data-driven robot learning.
Oh, am I presenting directly? Okay, yeah. I am. So, oh yeah, I have an adapter.
Yeah, it's going through.
Very different. Can we have a benchmark task on solving AV problems?
You want to zoom because you could present from your computer.
Yeah, I can try presenting from a computer.
Zoom.
Yeah,
Trust me, I will use this.
yeah. Okay.
Maximize it.
Oh, it's a current browser. Oh. Yeah, okay. Recording. I know. Sorry.
Maybe I'll ask one more question for Burke and so it seems like the benchmarks that you've been working on have been getting continuously more applied from like YTB to service robotics to recycling, which is much more industrially applicable. And I'm curious if that's intentional or if you see this changing like the novelty of methods or sort of who participates.
That was not intentional. Actually, when I was preparing this presentation, I was like, oh, okay, it's like these works seem to be within the same, can be presented within the same framework. So I think none of these, so the first part of the presentation, which was the benchmark parts, that was an intentional process. But I think this workshop, like this preparing this presentation helped me think like, what's the role of competitions maybe in this kind of benchmarking, or, you know, what industrial benchmarks might look like or can contribute to this as well. So yeah, it was not very intentional.
Okay, cool. And let me just open a few more things. Okay. That's okay. Whatever. Yeah. I think we want to remove this thing. There we go. Okay, great. So hopefully you can all hear me, and with some technical issues, my videos, half of my videos aren't working, so I'll try to pull them up later when it comes up to that time, but bear with me. Anyways, I'm excited to be here today to talk about some work we've been doing at DeepMind on robotic manipulation. This is work done with a large group of people, including Alex, Yusheng, Thomas, Toby, and Konstantinos. And as we've been talking about, there exists lots of different manipulation benchmarks, and they're all, you know, evaluating some different research questions. And they're all, you know, trying to provide a way for us to compare across different algorithms, different groups. So what do we want out of a benchmark? Not all benchmarks have to do the same thing, but what we were interested in is having a benchmark that's consistently replicable over time, because we want to be able to compare new methods to previous methods, check for algorithm regressions over time. So does the same algorithm perform the same way 3 months later when our code has changed, or maybe some new CUDA versions have been updated. And we want it to be easy to recreate as needed. So for example, if our objects break, can we easily get new objects? So we need to have detailed records of how to 3D print our objects, of how to set up all the cameras in the right places, etc. And we want to measure something informative. So what is informative might depend on the person, but for us, this meant a real world evaluation. And we want to have variants of different difficulty in order to get higher resolution about how a method performs. So not just one number, but a variety of numbers of the task at different levels of difficulty. And especially, we don't want our tasks to be solved with our current methods, because then there's nowhere to go. And finally, we want to avoid prescribing a particular approach, because the point is the task, it's not the method to solve the task, and we want to be able to try methods that are completely different. So not just like a neural network trained on images or whatever, but maybe different approaches entirely. And so our goal for this particular project was a task of manipulating objects that have sort of diverse picking and placing dynamics. So the name of our talk is Beyond Pick and Place, and I'll try to convince you of that for this particular task. So we want to have a large set of objects And I'll have different shapes that affect how a robot gripper would interact. And we want a very clear metric, clear task, because we want to be able to evaluate this in the real world using whatever sensors we have. So we don't want to have a full 6D pose detection of all the objects in the real world. So in this case, our task is to stack the red object onto the blue object in 20 seconds. And we have a green object as a distractor. And the task evaluation is just based on camera images of detecting whether the red blob is above the blue blob. So here, yeah. So, and then we also want this to be in simulation and in the real world. Those videos aren't playing, unfortunately. But first of all, I also want to say what our goal is not. So our goal is not about object semantics. It's not about, knowing that a spoon is for scooping and things like that. And in the work I'm showing here, it was not about a multitask setting, though we do have some future work looking at that. So the task is always red on blue. The objects are just these abstract shapes that affect the physical dynamics of the system. So now I'll go into these RGB objects, because this is kind of the main meat of the story. These objects are have like different affordances in some sense of grasping to start with. So if you think of a cube, you can pick it up from 4 different angles if you have a parallel jaw gripper. Well, if you have this trapezoid shape, there's the parallel sides that you can grasp on, but the slope sides you can't if you close your gripper there. So this is going to depend on your gripper, and it's going to depend on your shape. But this is something that means that the robot has to be aware of the shape of the object in order to interact with it successfully. And then for placing, we get this combination problem, which is that the shape of the object on the top and the shape of the object on the bottom both affect what kind of strategies are feasible. So if you have a trapezoid object on its side, you actually can't stack on it. The object will always fall off. So you'd have to flip that bottom object before you were able to stack. And this sort of almost cylindrical object at the top, if it's rotated, it might roll off if it's on the kind of rolly sides. So this is another way in which the stacking task, it seems very simple, but it kind of has this combinatorial problem of object shapes interacting with each other. So how do we get these objects? We start from a cube, and we have a bunch of different axes of deformation. So for example, the polygon axis is just adding faces. So you start with a cube, you get a pentagon thing, hexagon thing, all the way to a cylinder. Trapezoid, you're getting more and more less and less parallel on those 2 sides of the trapezoid, etc. And then we can take these deformation axes and combine them. So we have both of them happening at once, and we get these kind of double axes. So now we have a bunch of different shapes, 143 shapes, I think, from this that we keep, and they each have different physical properties. So with our shapes, our RGB objects, now we want to set up a task in order to stack them. And so the setup we have is we have a robot arm in front of a bin, and our observations for the task are the proprioception of the robot and 2 camera images here. So you can get a sense of 3D. And we use a Sawyer arm in this task, but in some sense, that's not that important. You could have a different robot arm. But what matters is that the objects are these RGB objects. And with our bin, we have slanted sides in order to have the object kind of come back to the middle so that you don't, you can kind of run autonomously. So we have an autonomous setup for resetting the environment in the real world by randomly replacing the objects, and they kind of come back to be in the workspace of the robot. So as I mentioned earlier, we don't want to prescribe any particular method. So as a baseline, we coded up a hand-engineered approach. So this is still from images because the task is from images, and it does red blob detection and blue blob detection. And it's just a state machine that goes towards the red blob, attempts to grasp, randomly rotates, attempts to grasp again until it's successful, then moves that to the blue blob and tries to place. And if it fails, it goes back to the beginning, tries to grasp the red blob again, etc. So this is kind of like the pick and place baseline. And unfortunately, videos aren't working, so let me try to pull those up. So where do I have? Oh yeah. Sorry, I had these all open, but then I had to quit Chrome in order to share my screen. And trying to find where they are. So anyway, so okay, so it works if the objects are cubes, but then if the objects are not cubes, you get difficulties in grasping. So this is our scripted baseline, but this is an object that has sloped sides. So it has to do a bunch of different attempts in order to grasp the object. Because this baseline isn't detecting the shape of the object, because that would, require training a shape detector. And if we have the on the placing side of things, if the base object is positioned along the edge so that it has a slanted side, this baseline isn't taking that into account. So it just tries over and over to place this kind of rolling object on top of the slanted side, which is unsuccessful. And then here's and this one is also very classic. This is our trapezoid. This is kind of our favorite object because it's so annoying to pick up, which is that this has these slanted sides. And if you don't know that you have to rotate 90 degrees here, you just fail for a long time. So going back to this, these slides, hopefully I've convinced you that these objects are this is significantly more difficult than handling cubes. A lot of past work mostly focuses on cubes, and this adds an extra. Okay, so grasping requires precise positioning and orientation. The objects have different grasping and stacking behaviors based on their shape. And then the slanted sides of the basket adds another level of complexity, which is that now they might not be flat at all in any direction. Once you have picked up the top object, you have to look at the relative position with the bottom object, because if you're not centering the centers of mass, it'll just fall off. And finally, we have this distractor object that not only is visually distracting, but physically affects what kind of behaviors you can do. So we have our environment, we have our objects, and now we can derive a number of different metrics. So from our objects, we actually separate out a held out set of deformation axes. So with our held out deformation axes, we have a very non-overlapping set of objects. And from the held out axes, we select 5 fixed triplets. So these are our real world evaluation object sets. The triplets are like the kinds you would have in a bin. So the triplet 1 has that trapezoid red object. And so we have these 5 triplets that we can always evaluate on in the real world. And we have the training objects that we can run on in simulation. And each of these 5 triplets has a different difficulty level. So unfortunately, they're not ordered in terms of difficulty, but so triplet 1, we have that trapezoid, which requires grasping at the correct angle. Triplet 2 has the trapezoid on the bottom object, which makes stacking difficult, and the parallelogram shape as the top object, which is difficult to grasp. But as you see at the top video of triplet 2, it can sometimes learn to flip the bottom object with using the top object as a tool in order to successfully place. Triplet 3, we have a long top object that has to have a good center of mass alignment. Triplet 4 is really the easiest one. It has a cube on top and like a almost cube at the bottom. And triplet 5 has this kind of rolling one. So we can evaluate all our policies on all these 5 different objects and get a more high resolution type of metric in terms of how many of these triplets can it actually solve. And then we can do mastery, where we train and test on the same triplets. This is easy. And then we can do generalization, where we try to train on objects from those train set axes of deformation, and then test on the test triplets. And this will test how much it can generalize to new object shapes that it's never seen before. And because we want to have real world evaluations, we have a real world setup and we have a sim that is matching as best as we can. And then in simulation, we can also do domain randomization to generalize better to the real world. So the approach we take in our first attempt at this is, pretty like straightforward in that we just want to have the best chance of success. So we take our simulation of the environment and we actually train from state on each passing in the shape of the objects. So if it goes from state, if your policy needs to take into account the shape of the object, well, I can't see it. So you actually have to have that as an input, or we can actually train separate experts on each of the 5 triplets in the skill mastery setting. And then for that state-based policy, we can distill it with domain randomization. So we take our state policy, we run it in the simulator, get images, and then train a new policy from image to action. And then we can deploy that image-based policy in the real world. We can collect more data in the real world, and then we can do offline RL for one step of improvement. So this is just one approach. This is a task that we're proposing, so you're welcome to have a better approach if you think there is a better one. And but from this method, which unfortunately videos are not working again, we get in the skill mastery setting, we get 82% success across the 5 triplets. So here, for example, I need the GIFs. Okay. So here we have, this is our method on the group 2, and we see that it has learned to flip this bottom object because it did train on this object set. We have where's the other ones? Maybe I don't have the other ones. Anyways, so I can come to me later and I can find these. It's a very unfortunate timing. So we have all these different triplets and we can learn to master them. But in the generalization setting, I think I have these ones available. We see that the generalist policy that was trained on the training objects in simulation, and then we just run it on the test objects in the real world without any fine tuning. It fails to deal with these shapes. So it gets about 50% success, which is not bad because it can do well on group 4, and it doesn't do very well on group 2 at all, which is the one with the slanted top object. So here there's a lot of space for improvement in this generalization setting. So in the skill mastery, if we look at the scripted baseline, which I showed at the beginning, that gets about 50% success. A human teleoperator gets about 47% success. I mean, that's not like a set in stone, but it's kind of hard to teleoperate a robot. These weren't experts. Our sim to real transferred policy got about 68%. And then if we take that policy, collect data on the real world and do improvement with CRR, which is similar to, it's just an extracritic method that's run offline, we get 82%. In the skill generalization setting, our sim to real gets about 50%. And then unfortunately, we had an older version of the policy collecting data because we hadn't had the new one yet. So with that data collection policy, we had 33%. And if we improved off of our 33% data, we get to 54. So there's quite a bit of space for improvement here. Looking at across the different objects, we see that some objects are obviously a lot easier. So triplet 4, it's about the same for the mastery and generalization setting. No benefit from training on those objects directly. But for triplet 1 and 2 and even 3, there's a huge difference between whether you trained on those objects or whether you did not. So takeaways is that we've introduced this RGB stacking task with our RGB objects. The objects are separate into training and test objects. So you can test on the test set and do skill mastery. You can not train on the test set and do generalization. And we get these different metrics for each of the different triplets. And so the mastery setting works pretty well. If you have access to those objects in simulation, you can train for a lot of data, but it doesn't generalize very well to new objects. So this brings up the question of whether we can quickly adapt in the real world on new objects if we have a generalist teacher. So we do have a version of this. So this was some follow-up work we did where we took our generalist policy and 40,000 episodes in the real world on triplet 1, and that's able to reach back up to the skill mastery performance. And it has learned to deal with this shape. Of course, it's not perfect. There's still some cases it can't deal with if it's too close to the edge. And sometimes it hits and terminates. And of course, 40,000 episodes is a lot. So hopefully someone can improve on that. Similarly for triplet 2, we can get a bit of improvement. It was 30% before, and then we collected about 40,000 episodes in the real world and improved and got to 54%. So it learns to flip the object sometimes, but sometimes it does not learn to flip the object. So it's still a bit of a not optimal policy. So all of this is open sourced. The objects are all 3D printed, so very easy to make new ones as they break, very easy to just download the STL, go to your printer and get more objects. The environment is all available in simulation. We don't have a robot cloud benchmark running for this, but that would be very cool. And we're paying attention to issues and stuff. So hopefully if you use it and you run into problems, we can help fix that for you. The setup for the real cell is also all in there, though that's a bigger commitment if you want to have the exact same bin and robot arm and stuff. Yeah, and I'm happy to take any questions, and hopefully I can fix the videos, find the other videos.
Thanks, Colleen. I actually have a question. I saw most of your videos were with Sawyer arms. I'm guessing you would have switched over to something like a Franca, and I'm curious if you were able to reuse any of the data from the previous robot form factor, or if you have thoughts on how we can adapt to hardware changes going forward.
Yeah, so we've switched to Panda now, which is slightly different, but we are in the process of trying to use that data, the old Sawyer data, on the Panda arm, though our process right now is probably more just do the sim to real process again, train in simulation with the Panda, and then transfer that with domain realization again to the Panda arms in the real world.
I think we have time for one more question. This one.
So I think this is really, really cool. I'm curious about if you see a way in which we can sort of try to run our policies on your robots, maybe sometime in the future. So I'm curious your thoughts of that.
Yeah, so definitely in simulation, it's easy. In the real world, you could contact us and we can try running it. We have lots of time to spare on the robot, so we'd happily try to run it. Trying to think if it's like, it's gonna be, there's probably version problems in there. Maybe we can try to get a Docker or something working. But yeah, definitely contact us if you want to run something.
Thanks, Colleen. Let's take a 15-minute coffee break and come back here on the hour. Okay. Now I've got video. Let's see, where's the- Hello. Let's see. Hopefully the people on Zoom can hear us. We will have Stefan going first. So Stefan, I don't know if you want to try sharing your screen and make sure that's working.
Yes, so at least I can hear you loud and clearly. I hope the others as well. You should now see me too. Nice to meet you. And I try share my screen. And you should now see the full screen. Loading. Maybe. Okay. Try again. Now it's loading, and you should now see my full screen presentation.
Yep, we can see it.
Okay.
Speaker view. I think we'll just wait a couple minutes for people to come back from coffee.
Hi, Stefan. I think we'll be waiting for like 5 minutes or so before we start.
Sure, sounds good.
Thanks. Okay, I guess it's time to get started. Welcome back, everyone. So in the previous session, we discussed some effort in benchmarking as well as some interesting benchmarking tasks. In terms of robotic development in the remote setting, there has already been some pioneering efforts, which we will be talking more about in this session. So let's welcome our first remote speaker, Stefan. Stefan is an assistant professor at KTH Stockholm, affiliated with the Wallenberg AI autonomous system and software program. He aspires to develop intelligent robots that can extrapolate experience across environments and tasks using the tools of causality and deep learning.
Well, thanks a lot for the very kind introduction and especially for the invitation to speak at such an amazing workshop. I think it's a great initiative and I look forward to the talk and the ongoing discussions. So today I will speak about the real robot challenge and how we can learn dexterous manipulation on real robots in the cloud. And this is in short what the real robot challenge is all about. So we basically provide access, we provide a submission system, and then people can submit their solutions to a problem, to a predefined problem, and we score their solutions, send them back data, and then can compare different approaches, how well they work on a standardized system. And this is actually what you see here from our benchmarks. On the right are some of these platforms I will describe in the following talk a little bit more in detail. So we have multiple of these platforms, and then we have 3D printed objects with different colors or only with the same color to host standardized tasks in the cloud where people can submit. And this is actually popular with some of these participants, at least in the very first challenge. So here on the left, you see Arthur Alsher, who basically got for his birthday a nice painting from his mom, because he was likewise so fascinated by the challenge as we are, and who later actually continued to work on some of these robots. And I hope to show one example of these collaborations in the future. Here in the talk, and likewise hope that if some of you are interested, we can potentially collaborate on some of these projects on these cloud benchmarks in the future. And so now in the next following slides, I will discuss a little bit more what some of these tasks of the challenge were and what are some of these outcomes and what was our motivation to actually host these challenges and what we want to get from it from a research perspective. And first of all, I have to thank an amazing set of collaborators. So hosting these challenges, building these submission systems, and then coming up with the task is actually a large group-wide effort, mostly from this people from the MPI for Intelligent Systems, where the platforms are hosted, and where the original development on some of the Open Dynamics Robot Initiative among Felix Grimminger and Ludovic Righetti took place. Other people who contributed significantly, especially in the proposal of these platforms and how the tasks are set up are from Mila. And so it's a rather community effort already. And I'm just presenting on behalf of all these people today. So what is our motivation? So in the past, we've seen a tremendous success of AI from playing Go to natural language translation, ImageNet classification, or even achieving superhuman performance in Atari games. However, all these tasks had basically one algorithm which was particularly designed for that task at hand. So most likely these algorithms would fail if they would be applied for any of these other tasks shown in the same image, even if they perform extremely well on one of these tasks. And so one key question is, how can we design algorithms which can actually extrapolate their skill to new and additional tasks which are slightly related and which have a compositional nature? And one of these problems we are in particular interested in is so-called causal representation learning. So we thought that causality should help in some of these generalization tasks because it can provide a language, how to formalize interventions, to build models that are robust. And one of the key problems, however, is that mostly in causality, we already observe the variables of interest directly, while in robotics, we only observe images, for example, or low-level sensor data, for example, the fingertip sensor. And so we would first need to learn representations in a low-dimensional space, which somehow categorize and learn representations which correspond to our human-level scene understanding in order to then build different downstream tasks on top. So for example, if the task for the robot is to sort all objects by color, then we would expect that only color and the position should matter. While if we task the robot with sorting all objects by shape, then only position and shape would matter, while color would be a nuisance factor. So if we would learn these factors, which would correspond to our human level scene understanding, like color, shape, and location in this latent representation, such that then we can only use the factors of interest for different downstream tasks and recombine them, that should enable us to build smaller models which are more efficient, more interpretable, and in particular more robust to some of these nuisance factors which should not matter for the problem at hand. But more importantly, we would actually argue that generalization is likewise about reusing and repurposing skills. So here, for example, we see a robot on the left, which is able to pick up a red cube and push it away. And we would say that if we would actually learn the skills to be able to do the task on the left, then our mechanistic understanding of this world should be sufficient to actually likewise perform the task on the right, which is basically restacking and reversing a tower. And with control theory, that's possible to do, but then you would need to generalize across all these shapes or color or color settings or different form factors and frictions. While we would actually aim now in this challenge to partially learn all these skills. So can we learn and to reuse and repurpose skills for different tasks by learning them, for example, from images or with object tracking. And depending on what we want to do, so if it's from image tracking or just from images, we actually provide different tasks and leaderboards in the Real Robots challenge. And what is the inspiration for this compositional nature? So we know from psychology, for example, from Alison Gopnik's work, that interventions are key to learn causal relationships. And what is actually interesting is, or one of the earliest examples, at least with which I learned, is actually the example of Lego blocks. So here, for example, we see small children using Lego blocks to build different structures. So on and they have different sets of blocks with different colors, with different shapes, and they can build, for example, a castle or a tower on the right. And this provides an actually infinite large space with completely different tasks and goals by building these different shapes. And humans or children generalize very well within this world by repurposing previously learned skills in a similar but slightly different environment. And this is something we wanted to recreate basically with some of the setups we built, and which was a clear inspiration for some of these robots. So here we see basically the robot, which is given a couple of red blocks, and it's tasked with building a green tower. And why is that needed? That is needed because if we play, for example, different Atari games, we actually don't know what is the underlying structure between two levels of an Atari game, or even between different Atari games. So it's very hard to actually make systematic progress towards investigating the different generalization capabilities of agents. While here, which is called causal world in our simulator, we have a parametric robotic manipulation environment where the environment changes are defined as interventions on any of these defining variables. So we can intervene on color, friction, mass, gravity, and then investigate how an agent trained on that system is generalizing with respect to one of these variables or multiple of these variables as plotted on the right. And for this, we likewise provide different task generators in the simulation environment, ranging from very simple, from like pushing a cube to lifting a cube to stacking a cube to stacking multiple cubes to building arbitrary shapes, which some of them might even be suspended in air. And this provides this infinite task space, which is inspired by this Lego environment and which is extremely difficult. And this is actually some of these underlying tasks here you see are basically the tasks underlying this Real Robot challenge in order to make progress towards this reusing and repurposing skills across different tasks. However, what has to be said is that this task world, even though it's inspired by this simple Lego world, is extremely hard and challenging. So right now, what we are basically able to do is, for example, at most, is stacking different cubes or being at least robust to distractors in the scene. So if you, for example, have the task of stacking two particular cubes or pushing one particular cube while there are other cubes in the scene around. Already this task is an extremely hard one for current reinforcement learning algorithms. But how does this actually look in the real world? So what we have here is our tri-finger robot, which has 3 fingers, each with 3 degrees of freedom. it's relatively easy to rebuild and relatively cost effective. It has 3 cameras around, so which record the scene from different angles, which work on 50 hertz for the camera recording, and the robot itself works on up to 1,000 hertz. Despite the fact that the 3D shells, these black colors are 3D printed, it's pretty much unbreakable by the user. So it would beat me in arm wrestling, for example. And we provide an easy to use interface, which allows you to code both in C++ or Python, depending on your choice. And the whole setup is based on the open torque controlled modular robot architecture, which was provided as an open source robot initiative. So here you see basically the corresponding quadruped, which is now expanded and which is fully detailed on this homepage of the Open Dynamic Robot Initiative, which is basically a collaboration between NYU and MPI for Intelligent Systems. And what you see is basically that one of the legs of the quadruped is per se basically one of the arms of these manipulation platforms. So if you build and want to get some of these platforms, you can use them, for example, for a quadruped, or you could use them for a manipulation platform, depending on your interests. And what we see now here, hopefully in some of these videos while they load, is actually that the capabilities of this real-world system for fine-grained and dynamic manipulation. So on the left, it should just, you see the task base where it's reaching around. On the bottom left, it's taking a pen and writing. On the top right, it's basically throwing a ball. And on the bottom, on the lower right, it's basically balancing and putting up a rectangular shape. And so we can see that basically the robot has quite a good workspace. It is able to do dynamic locomotion. It's able to do a little bit of fine-grained manipulation. And yes, we can use it for a couple of challenging tasks. And what you see here is basically going away a little bit from this one robot tri-finger, which is placed alone on a stage, towards a setup where we actually have a benchmark of multiple of these platforms in cages. The cages are there to provide a consistent lighting environment such that every platform has the same light, basically undisturbed from the outside, and to provide basically a fair comparison between platforms. There might be still slight differences between platforms, but generally, at least to the eye, they look very same and very controlled. And we have 8 of these platforms running with spare parts for multiple more, but actually they are very robust. So repairs currently are actually minimal. And we are still open to suggestions, either from the setup. So what you see here are some of these objects which are 3D printed and colored. The colors is there on each of the sides to provide object tracking. So while we can and offer to throw in basically any object in order to get a fine-grained object tracking, some of these colors are necessary, and otherwise I at least would not directly know how to do that. What is another interesting aspect is that the robots don't have automatic resetting, for example. Basically, your end position is the new starting position. So what are some of the tasks we provide the participants? So here you see the task of stage 1 and 2 of the first real robot challenge. So why you see here basically this transparent object is that it's overlaid with object tracking. This is why it's like with a little bit wriggling, because the tracking is provided every 10 hertz, and so it's a little bit wriggly. And here in the first stages, it's basically bring a cube to a target location in this robot arena, which is a relatively large object. And in the second stage, it was then already a little bit harder to bring this elongated, smaller object towards a target location. And some of these stages were actually that then orientation mattered at the beginning. It didn't matter at the beginning, but in the later levels, actually the orientation of the cube or this elongated object likewise mattered. And it turned out that, for example, bringing this cube to a target location is much, much more simpler than, for example, this elongated object. And the reward was basically how much of the volume or the overlay, if orientation didn't matter, you actually filled with one of these tracked objects. And so here you see again this object colored position. We originally wanted to have a later level where it should be about writing your name or writing basically that you won. So here this is something we tried to program, but no one was actually able to advance to such a stage to picking up a pen and writing on a piece of paper that I won or your name. So we had to stop it at basically pushing and moving around objects. Now, afterwards, we actually hosted, and the participants continued and provided a large-scale evaluation on the real system with basically a grid search over all the submissions. And there are multiple possibilities to consider. So here, for example, just in simulation is shown that what participants used, and they actually used different grasp strategies. So for example, here on the left, they basically put the fingers such that the force was pointing to the middle, so they didn't put it on the center of the sides, which they did. One team did, but very few did. Or here they actually put 2 fingers on one side and 1 finger on the other side. So different strategies were actually applied by these different teams, and you can now ask, okay, what is the best grasp strategy to, for example, replace then the object before putting it to the final object? And they run a large benchmarking study with over 20,000 experiments on the real system, but unfortunately, to some extent, the conclusion from this experiment on the real system is inconclusive, in the sense that basically every grasp strategy is better than the others in at least one setting. And here, the investigation was basically by changes, by differences and changes, because we don't have an automatic reset. We basically compare relative distances. So relative distances, for example, in orientation between the initial state and the end state, and not the absolute differences. But from this large experiment, over these 20,000 submissions through the cloud system on the real platform, unfortunately, there was no conclusive evidence, at least for what of these control strategies with grasping strategy worked best. And the year after, there were actually more and more learning-based strategies. So in the first year, we saw in particular basically control-based strategies which were winning. Now, the year afterwards, there were more and more learning strategies. And what is likewise interesting is that basically the simulator which was provided works quite well, in the sense that the learn policies are able to transfer to the real system without any fine-tuning or algorithms such as domain randomization. But the simulator, which was based on PyBullet, was actually one of the main limitations, in the sense that the simulator is still quite slow. And we will see that some of these newer approaches are actually much more capable. Here you see the winning policy from one of these benchmarks, how it's orienting and pushing around the large object. And that is some of the interesting behaviors which came out of some of these benchmarking studies, that it has to first replace the cube in order to bring it in the right orientation, and then move it actually in the location in space. Moreover, nowadays, so as mentioned, there are more and more simulators coming up. So there was a collaboration with ARSO, who I mentioned at the very beginning, and NVIDIA and University of Toronto, which trained in ISACSim, which is the GPU-compatible NVIDIA simulator. And they actually managed to get very interesting behaviors by training on such a efficient simulator, on GPU-compatible simulator. So one of the recommendations I would take away from some of these challenges is that actually we see only very interesting learned behavior if we have simulators which can be trained for a very long time with billions of steps. And then actually you see a very good and fine-grained manipulation, which zero-shot again transfers to the real system. So they submitted, having only trained in Toronto, to our cluster in Germany without any fine-tuning, then on the real system again. And that is quite interesting that, depending on the time you can train with the simulator and how efficient the simulator is, you actually see much more interesting and fine-grained manipulation behavior. And now what we had actually this year, so this was the Real Robot Challenge 2, what we had actually last year, which was the second Real Robot Challenge in 2021, in this second stage, is actually much closer again to this causal world setup, to this compositional generalization. So there, what we wanted to do was, after the first stage, to go towards this causal world setting of using blocks to build things. And here the task was to basically place 2D shapes in the arena using these cubes, which all have the same color. And then the reward calculation for the final task would basically how much of the blue color is in the particular area in the arena where the shape should be. Unfortunately, because you need to do this from images, actually no team which participated was able to perform the task or even perform something meaningful or interesting on this setup in the real world, which basically shows that we just selected the task as way too hard. This I would actually jump in due to the time period. Basically, what it allows for us is to investigate now different out of distribution generalizations for learned representations on the real system. So for example, if we train structured representation or this causal representation learning at the very beginning, how well do these representations then train how well do these representations with a trained policy generalize to out of distribution tasks, either from out of distribution from the encoder or the trained policy, or even on the real system. And having such a setup where you can focus here, for example, only on the object color is a very cool thing to actually investigate and provide a systematic investigation of these properties of these learned representations for generalization. So what, to conclude slowly, what are some of these takeaways from organizing the challenge? So it's actually fairly interesting that I think that the submission system worked really well. So this cloud-based setup that people can just submit and debug the code locally and then resubmit again works really well. At the very beginning, there was a couple of interactions with the participants on the submission system still, but nowadays it's really running smoothly and it's as easy as submitting the training of a neural network to a GPU cluster. So it's really nice. We saw similarly to other submission deadlines that submissions closer to the deadlines increased significantly. And at the very beginning in the first year, there were some design modifications necessary, but afterwards we actually changed fairly little or nothing on any of these robots. And now they're running, very long, for a very long time without any repairs, and we don't have much to do with maintenance, for example. What one of the key things is, and where I'm quite excited about, for example, this IsaacSim or new initiatives, for example, the hope that DeepMind would release at some point a GPU-compatible Muchoco simulator or Prax from Google Brain, is that we really see that these GPU-compatible simulators have the ability to show completely different learned skills and enable the learning of different skills. And that this is especially interesting when we go to learning directly from images, because unfortunately object tracking is really difficult to get working reliable, especially if orientation is included. We are very open for any feedback on different proposals. On the right, you see basically the quadruped or the biped. So if you're interested in some of these setups for having such a robotics in the cloud submission system for them, or if you want to have different objects or think different objects in this arena are very much interesting for the community, please reach out to us. There's likewise now these data sets from these challenges available. It's open source. And the real world data set collected from these robotics benchmarks is actually part of this year's challenge, which is a Europe's challenge again. It's the third iteration of this real robot challenge, and this year it's on offline RL. So basically we provide the same tasks again in the same data set. So we provide trained policies which are performing the task, for example, pushing on the cube to a target location or lifting a cube to a target location. And we provide these trained policies as well as these offline data sets. And the question is, can you come up with a better policy which does it faster? Using some of these provided policies or some of these provided data sets. So this is starting nowadays. Basically, the announcement on Twitter should soon be out. And with that, I can basically refer you to some of the publications we've had for this setup, for example, the robotics platform, and would be very open to one or two questions if we have time for that.
Yeah, thanks, Stefan, for the talk. Is there any questions from the audience? Okay, I have a question for you. So what would you say is the importance of the simulation part for the real robot challenge? Like, for example, in the offline RL challenge that we're gonna introduce soon, what do you think? Like, is it a necessary part for the algorithm to work on sim first as a sanity check, or like are they like parallel threads with the real robot part?
I would say by now it's pretty much parallel. So we only use basically the simulator such that you get familiar with the interface and these things. But there would be no, you could directly train from scratch even on the real system if you would like. Yeah, we actually hoped at the beginning that the real data would improve the simulator drastically at some point. But it turns out that this is actually not necessarily needed. What is, however, very much interesting, I think, in training in simulation is that it's so much faster, potentially so much faster than real time. So if you use these GPU compatible simulators, you really see, yeah, very fine-grained manipulation skills, which would take probably too long on the real platform to actually obtain. So this is something where I see the opportunity of the simulators for training itself, for lifting or pushing an object. You could directly learn that on the real platform.
Thank you. Liam, do you want to ask your question?
Sure. Really awesome project, Stefan. Thanks. I'm sorry if you mentioned this and I missed it, but is the reward function and is the reward part of the environment, or is it something that the user can somehow specify? And then in the like offline RL case, are the rewards embedded inside the data set in some way?
Yes, so these are good questions. So for example, for these first projects, we basically define the reward for these leaderboards, but the user has full control. So you could basically say that you want to use another reward for training or learning, so you can do whatever you like. But finally, how we estimate is basically that is defined by us, and that is, yeah. Depending if you want to change some of these settings, I'm more than happy to actually try that out and provide access. And yeah, I think you are one of the creators of Ducky Town, no?
Yeah.
That is very cool. That was actually one of the inspirations for us. So thanks a lot for hosting that.
Yeah. If we don't have any more questions, let's thank Stefan again for the talk. And let's welcome our second speaker, Liam. Liam is an assistant professor at the Université de Montréal, where he leads the Montreal Robotics and Embodied AI Lab. His research focuses on building suitable world representations, modeling uncertainty, and building better workflows for teaching robotic agent new tasks. In addition, he leads the Ducky Town project that focuses on making state-of-the-art robots for both accessible and fun.
Hi, hopefully you can see everything and hear me and everything.
Yes.
Okay, great. So thanks so much for inviting me. I'm jealous that I'm not there with you all in person. I actually did manage to get COVID this week. So even if I had planned to come, it would have probably been kiboshed. And also, maybe I'll just say at the outset, like finding my brain is working a little bit slower than maybe normal. So bear with me if I'm like having trouble finding words or expressing myself a little bit. So yeah, what I want to talk about today is the Ducky Town that Stefan just actually alluded to, Ducky Town in this AI driving Olympics competition. So I thought maybe I'd start with a bit of just the history of the project. So this project started as a class that we developed at MIT in 2016. And I'm not sure if she's in the crowd, but Victoria was one of the students in the class, and she's one of the co-organizers of this workshop. She was actually one of the very few number of undergrads that we like accepted into the class because she is so exceptional, you know. Anyway, so we designed this, like the project, the purpose of the class was to design this autonomous car system basically from scratch. And then the class culminated, hopefully this isn't too loud. The class culminated in a final demo, which was in a big hockey rink, and probably Victoria still has nightmares about this because we gave every single person who came by like a ducky, and then there was just like squeaking duckies for like 5 hours. But it was a cool experience. I hope that Victoria also feels that way. And I would have never dreamed that like whatever 6 years later I would still be talking about duckies and things like this. But the objective of the class was really to see to what degree we could like distill the autonomous driving problem down into something small and preserve as many of the real challenges as we possibly could. And I think, in some ways we were successful. So following the 2016 class, this thing kind of took on a mind of its own. We open sourced all of the materials, and so there ended up being classes around the world. This is like a very old map. There's now sort of like many more classes and people that are using the platform than I can keep track of anymore. But it became also this this kind of outreach project in the sense that it was meant to be something friendly and fun at the same time as being like educational and pedagogical. And I think this kind of struck a nerve with some people, that it was like it's kind of cute but serious kind of approach. So I'll just describe a little bit what the actual platform is, and then we can get into maybe more of the details about my thoughts on the benchmarking and the use of the cloud. So really there's two components. There's the robot that moves that we call the DuckyBot. So this is a simple two-wheel differential drive robot. And then there's the environment in which the robot operates, which we call the Ducky Town. And this, although it's created from exercise mats and duct tape, it's very formally specified, and it's modular in its design. You can sort of like assemble the tiles any way that you want, and you can make things more or less complex by adding more agents, more complexity to the road topology, more objects in the way, and other things like this. So the robot itself is, there's been a few different iterations. This is the newer model, the blue one you see here on the left, but it's very simple. All of the sensing is basically done with one fisheye camera that's on the front. There's also DC motors that have wheel encoders. There's a battery. There's LEDs that are used for communication and other things. And then there's some kind of computation. We started with the Raspberry Pi, and now we have a Jetson Nano. And then, of course, there's the duckies, which are like the passengers or the customers, I guess, which are essential yet not essential. And then the town itself, as I mentioned, is composed of these modular tiles that can be assembled. And so there's this sort of floor layer where we add the tape, and then there's the signal layer where we have traffic lights and signage and other things like this. So in around 2018, so I'd already started at the University of Montreal, we looked at this platform and thought, well, wouldn't it be interesting to see how the community can do on this problem? If this is like very, very easy or very, very hard. We'd been using it in our classes, but we kind of wanted to open it up to the community at large. And so we applied to do a competition at NeurIPS in 2018. It was also fortuitous that NeurIPS happened to be in Montreal, which is where I was. And then ICRA also in 2019 happened to be in Montreal, which is where I was. So we hosted this competition, which I think, I might be wrong, but I think it was the first kind of like real robot competition at NeurIPS. But I might be wrong about that. Apologies if I am. And a lot of thought and effort now went into the building of the infrastructure for this competition. And now we've been continuing to run this competition for the last 4 or so years at ICRA and NeurIPS and kind of other places also, with a pause in the middle because of COVID. So so what's the purpose of this AI driving Olympics thing? So I think this is part of a larger effort that I've started to push on in my lab about the importance of evaluation and benchmark. And I think to some degree, this has really been inspired by the reinforcement learning community, which has really made significant progress, I would say, in pushing for scientific rigor in reinforcement learning. And I think that there's still some work to be done on that front in robotics. Historically, maybe getting the video of your robot doing the thing was enough to get your paper accepted at a robotics conference, but not sure that that should really be enough. But certainly reproducibility in robotics is even more challenging, I would say, than the just reinforcement learning case. So we've been hosting these workshops at IROS to try and think really hard about how to evaluate progress of the self-driving cars in particular, and also to think about the broader impacts outside of just the traditional metrics that we think of, which are kind of overly simplistic. But I mean, over the course of the thinking about this, I think the main conclusion that we've come to is that building robot benchmarks is really hard. I think probably Stefan would tell you the same thing. There's a lot of dirty details in robotics, and I think these dirty details can't just be swept under the rug. If you're just sweeping all of the dirty details under the rug, then it's not really clear to me anyway, how representative of the real world that benchmark really is. There's also this aspect of robotics that it's like a closed loop thing. It's like a thing where you take action and then something happens and then you get sensor data. And so this thing has to happen in closed loop. The other existing robotics benchmarks, which are mostly focused on perception, don't consider this aspect at all. Although those benchmarks like Kitty and things like that have had massive, tremendous impact on the community, there is still something lacking there in terms of the action aspect. And then there's the complexity of the tasks that we want to try and do with robots, and how we can faithfully build benchmarks that represent that complexity. And I think the example that Stefan showed is also a really kind of clever and beautiful example of that, in that it's a kind of simple setup, but you can already see that even with such a simple setup, the complexity of the type of tasks that you can specify and things that you can do is already so enormous and rich. So what we tried to do with IDO was really not ignore any of the ugly stuff. There's also, and I think Stefan touched on this, is that we want to allow the maximum flexibility in terms of what is imposed on the developer. We don't want to tell the developer how they have to do things like this or like that. And then also, derived from the origins of the project, we have a huge emphasis on accessibility. And I think the cloud aspect has a huge role to play in that. So the software should be super easy to use and get started with. The hardware, in terms of both the robot and the environment in which it operates, should be really easy to get, should be inexpensive. And on this front, I think maybe Stefan and I have a slightly different definition of inexpensive. Our environment is maybe $300, but 5,000 is not so bad. But this is these things are going to have a massive impact on how on the different demographics and folks that are going to be able to engage with the benchmark. And also, finally, it should be easy to get your agent evaluated in some kind of scientifically rigorous way. And also, I would say, in 2018, it was maybe the writing was on the wall, but I would say it was not super clear what the role of learning was. And so in terms of the not imposing anything on the developer, we wanted to be able to very gracefully handle vastly different kind of paradigms and approaches to solving this seemingly simple autonomous driving problem. You should be able to easily compare apples to apples, fully end-to-end learned approach with a more classical engineered approach with the typical robot abstractions. And this is not so simple, I think, because there's sort of these big kind of divides, and these maybe is dirty details, but somehow the details matter. Like the people who are the traditional roboticists are typically used to working in a certain kind of software paradigm. So I've got like an example here, like publish, subscribe, ROS. You know, this is the world that we're like very comfortable in. And then the folks who are really comfortable doing reinforcement learning and these kind of paradigms are much more comfortable in this kind of like Markov decision process, OpenAI gym kind of world where you can step the world forward with an action and receive you know, an observation and reward from the environment. And yeah, so I think I see the beauty and the value in the latter in terms of how clean it is in terms of the distinction between the agent and the environment. But there's some aspects that in some traditional kind of reinforcement learning style approaches that are really missing here. And there's the, you know, the thing that like the real world doesn't actually like step whenever we take an action. It's like it's doing things all the time, and we need to like, there's some kind of aspect of statefulness and the aspects of latency and other details that are like crucial in robotics are not necessarily reflected at all in this more like OpenAI gym style interaction. So we tried to think about how we could kind of like put all these things together. And then around like 2000, I mean, much before, but this didn't really hit the robotics community until like around the time that we started to build this NeurIPS thing. And now it's like almost seems obvious or whatever, but that containerization was kind of the key for this. And the reason that this is so important is that it enables this very clean distinction between the agent and the environment that it's going to operate in, that still enables you to preserve all of the kind of the ability to do things in the traditional way that you would like, but that also admits this new kind of more OpenAI gym style paradigm. So this took quite some effort to get it right. I think we're pretty much there, but the idea that you're going to package up an agent as a Docker image, and that it's going to interact with this other packaged up container that's an environment image. And as long as the interface between these two things is very well specified, and I think we can pretty much just use what the Markov decision process, you know, like tells us, which is that actuation commands should go from the agent, you know, and that sensor data should be the thing that's returned. As soon as that interface is like very well formally defined, then you can swip and swap the things on either side very easily. And this is the key. So now it means that I can take my one agent and I can run it against different versions of the environment, whether that's a simulator, whether that's in the cloud, whether that's on the real robot in your own lab, whether that's on a real robot in a remote lab, it doesn't matter. None of that matters. And also it means that on the agent side, you have the flexibility to basically use whatever kind of paradigm you want. We can build baselines that use OpenAI gym style, and we can build baselines that use a more traditional robotic style. Okay, so I won't drone on about that for too long. So very much inspired by like Sean Wilson and Magnus, who's the next speaker, we built these remote labs where we could actually try to evaluate our agents in the cloud, where in the cloud in this case just means remotely. And this is also kind of a massive undertaking. Here we use this camera-based, so all these like yellow, gray poles and stuff and colorful poles are like cameras that are being used as a part of a localization system. And so actually this auto lab in and of itself is actually like democratized, and you can build one of these in your own environment. You don't need any expensive infrastructure like Vicon systems. And so now this becomes like a tool that's part of our, part of our holistic system. And so, yeah, the thinking about the simulator part is also something that we thought like very hard about. I think, again, here, there's kind of a trade-off between the realism and the speed with which you can use the simulator for training. And I actually would also be kind of interested to try and get our simulator up on that Isaac Gym thing to see how, to what degree we could parallelize it. But there's a lot of like little details that in these simulators matter a lot. And it's actually like how well things are rendered and things like that is much less important in our experience than modeling the latencies and the blur in the camera properly and things like that. So like these kind of dirty details are essential in terms of actually getting real usefulness out of these simulators. We also like start to think about this not as just one simulator, but as a simulator family. And maybe as a quick aside, I think an interesting line of research that we've been pursuing in my lab is also trying to actually formalize the usefulness of simulators for robotics tasks. It would be certainly would be nice if somebody handed you a simulator and a task that you could have some way of like knowing or extracting only the useful information from that simulator. So I mean, so now I'll talk about some of the other like tools and things that we provide as part of the benchmark. So of course we have like annotated data sets and logs from this thing, having been a project now that's been ongoing for over 6 years. So we have quite a lot of diversity in the data set since it's been used kind of all over the world and for quite some time. And so you can do all the like standard things like train perception models pretty easily. And so we provide these baselines that people can use to get started. And these baselines, they span the gamut in terms of approaches. Like our Duckytown code base that we use for education is much more of a traditional robotics pipeline that contains all the standard robotics abstractions like perception and state estimation and planning and control. But we also provide baselines for doing like the newfangled machine learning, deep learning things like end-to-end reinforcement learning, imitation learning, both from logs, from simulation, etc. And we worked extremely hard to try and make this easy to use and easy to interact with. So if you want to get started with this benchmark, you pretty much this is the workflow is the following. So you pretty much pick which like template or baseline you want to start with. You check out that Git repo. Then you can build and test your agent locally and test it against a simulation locally on your laptop. You can test your agent on your robot, or you can submit it to the remote lab to have it evaluated remotely. And then finally, once you're like happy with the way that it's performing, you can make an official submission to the benchmark where it'll be like actually properly evaluated and you'll get a score. And then you'll get to see all of the debugging data. And for each one of these things, it's just like we built this kind of shell API that allows you to do all of these things like very easily with one line on the like command line. So in 2021, which was the last iteration of this, which is at NeurIPS, we had 3 challenges. One was the lane following, where you're the only agent on the road and the road network has sort of varying degrees of complexity. One is lane following with intersections, where you're the only agent on the road, but you also have to worry about navigating through intersections. And then there's the lane following with vehicles, where there's other agents on the road that you have to worry about. And in terms of evaluation, we had 4 metrics. There's the distance you travel in a fixed amount of time. There's how long you survived, which means you didn't have some kind of catastrophic failure. And then there's the lateral deviation, which is how much you deviated from your lane, and how many major infractions you had, which is like crossing into the other lane completely or hitting something. And maybe I'll like say one thing about metrics. This part in and of itself is extremely challenging, mostly because of like the Goodhart's law problem. So what we've seen is that people tend to, when these metrics are specified in this way, people tend to overfit to the simulator, to the whichever paradigm that they're like using for development. And this is not great. So I'm actually for future versions of the benchmark, I'd like to move away from these types of metrics and actually just have a progressive kind of curriculum in terms of complexity and difficulty of tasks. And you have to have just some baseline performance in order to pass that level and get to the next level, I think is a better option rather than these metrics that people can like hyper optimize and stress about. So this is the winning submission for lane following from 2021. And I would say what's interesting about this is this was a primarily reinforcement learning based approach. And this is the first time I would say that a reinforcement learning based approach really dominated the rest of the approaches. And although maybe it's sort of hard to judge from the way that this is operating, like I would say this is better than I could do myself with a joystick. So we finally reached what I would say is like superhuman performance with a reinforcement learning based approach. So maybe in the last like couple minutes, since the theme of this workshop is really learning in the cloud, I'll just offer some thoughts on like what's the value of the cloud for robotics in our particular use case anyways. I mean, so there's all the easy stuff, the normal stuff that we already know and think about. So we can train a model from static annotated data sets. That's really straightforward. Slightly harder is to train agents that interact with environments, because now you have to like have these two components that talk together somehow. And we have our own solution to that, where these interfaces are very formally defined, and actually the way that they interact is through like actually like queues, like they write to disk. But there's lots of other ways that you could do that. Harder still is actually like doing rigorous evaluations in the cloud. This has actually been the majority of what we've used the cloud for so far in this project has actually been to do evaluations and not for people to do training, unless people are doing that, you know, on their own in their own little cloud. And then I guess the hardest thing is to do this evaluation of agents on real physical hardware in the cloud, where that means like remotely. And we're still, I mean, I think we've made real progress on this front, but we would still like to further automate that process. And so these are the things that you can do. And then what are the benefits? Well, I mean, I think, yeah, owing back to the origins of the project, there's clear benefits in terms of democratization. When all of this is happening on the cloud, it makes it much more accessible to everybody around the world. And I think that this is really should be like a key motivation for us. And then also it enables this level of scientific rigor in terms of the reproducibility. You should be able to, in remote labs or on the cloud, be able to have very reproducible conditions so that you can actually evaluate agents in some kind of rigorous way. And I think this is essential for robotics to like actually progress in the future. Maybe one last note that we've also like gone back to our education roots, and we use all the same evaluation infrastructure to evaluate as like auto grading now in our massive online open source course. So this will run another iteration of this in the fall. But yeah, so there's also this this thread that continues. So thanks to all, I mean, this is like a tiny snapshot of the people who contributed. Maybe these are the people who contributed the most in the last year, but we've had lots of support from AWS, AI Crowd, Motional, which used to be Aptiv, which used to be something else, I forget. Also Swiss Re, which I don't have on the slide here. And this is a collaboration with many, many universities and partners, ETH, University of Montreal, TTI Chicago, and others. So that's all I had for today, and thank you for your attention. And if there's any questions, I'd happily try to answer.
Yeah, any questions?
Thanks, Liam. My question is about you mentioned that for the first time an RL method is performing the best on one of these benchmarks. I'm curious what the tipping point was, do you think? Was it availability of data or a simulator or maybe a better reward function? What was it that led to RL suddenly performing the best?
Yeah, that's a really good question. I think the overriding factor in this case was getting the reward function right. And it's one of those things where like, and honestly, if you look at some of those other like Isaac Gym things, like, yes, they're able to learn extremely well, but also the reward function that you have to give is like extremely dense and extremely tuned. And I think, unfortunately, that's also the case here. It's not so easy. Like, it's easy to think that you can specify a reward function that's just like you get reward for going forward. But like, I'll give you a funny example. So like, you can actually sort of seem like you're going forward if you just spin around in place. And so like the very first iterations of people that tried RL, because the reward function was like just that little bit hackable, that you got a tiny bit of reward for just spinning in place, all of the agents that like tried to use RL were just like spinning in circles. So yeah, that's what I mostly chalk it up to. There's certainly the aspects related to the simulator are crucial. And I think the modeling of the things like blur and latency and getting those parts right, those also significantly contributed to the failure of the RL based agents in the early going as well. These were just unmodeled effects that caused the sim to real gap to be just too large to cross.
More questions?
Hey, Liam. A question on how do you handle submissions that are bad, I guess, right? So when you get a submission in remotely and it is going to slam into a building, right? It's going to take out one of your ducts. Do you catch that ahead of time? Is it a consequence you deal with after the fact? How does your remote operation system handle that?
I mean, so that's where the fact that they're like, I mean, we don't condone any injuries to duckies, but the fact that this is a very small and, not life-threatening situation means that we kind of don't need to worry about that maybe as much as you would as if this was like a full-scale actual thing. And that's kind of one of the nice aspects here is that, yeah, as long as we have like the ability to stop a run as soon as it goes south, that's kind of sufficient.
Cool, thanks.
Yeah, if no more questions, let's thank Liam again for the cute project. And let's welcome our last speaker, Sean, which is in person. And Sean is a senior research engineer at Georgia Tech Research Institute. His research interests include remote access, robotic hardware, and control of multi-agent robotic systems.
How do I need to switch over to the telesystem switch it? Do I take that?
Yeah.
Awesome. Fantastic. Oh, cool. I love when stuff just works. Okay, good. All right, great. Thanks for the introduction. So my talk is going to be a little bit different. It's going to not really regard benchmarking so much as it's going to talk about how do you actually implement a cloud robotics system. So as a foundation, I'm going to talk about the experience we've had developing the Robotarium. This is a remote access multi-robot testbed where we don't have a task in mind. We let anyone
all over the world upload their programs to run and test on our hardware. Yeah.
We're not seeing the slides on.
Cool. Yep.
Are you presenting on Zoom or are you?
Oh, no. Sign into Zoom on this? I might have to install Zoom on this, unfortunately. Yes, I will.
Does it work from your browser?
We'll find out. Yeah, let's do that.
No.
Cool. That was me.
We could just use this, I guess. Yeah, because we can kind of see the slides from here.
You sent me the Zoom link, didn't you? I think. Sorry, I have to.
Yeah, if you think this will be too hard, we'll just,
I'm not think I can get it right now.
Got it.
Yeah.
Meeting is being recorded. Meeting is being recorded. Meeting is being recorded. Meeting is being recorded. Meeting is being recorded.
Sorry about that. Okay. Share screen. Yeah, you can. Sure, you can have all those things. Sure, have the entire screen. That's fine. Wonderful. And I'm muted. I don't think I have any feedback. Let's see. Are we good on Zoom now? Fantastic. Okay. All right. Sorry. Oh, gosh. Thank you for telling me about captions and subtitles. Okay, cool. So, yes, I'm going to talk about the Robotarium, and I'm also going to take advantage of the workshop and talk about things that we've learned and stances that we have on cloud robotic systems, in hopes that you guys will push back and we can have an argument later on. So, to lay the groundwork, the Robotarium is a remote access multi-robot test bed. So to access it, users from around the world, you go to robotarium.godtech.edu. We only ask you who you are, where you're from, what you're doing with it. We don't vet anyone. And at the end of the day, you're sending velocity commands to robots. You can use one robot, you can use 20 robots. We don't care. The test bed itself here, pictured on the right, is just a converted classroom at Georgia Tech. And to give you an idea of scale, the actual ice rink bathtub test bed is about 4 meters by 3 meters, to give you an idea of how big this thing is. To leverage it, like I said, we have no tasks in mind. At the end of the day, you have to send a velocity command to the robots. So it's on you. The development cycle is pictured here. Orange here is user facing, blue is our side facing. So at first you just have to develop your theory, right? You have to come up with what you want to do. It can be one robot, it can be for educational purposes, it can be research, whatever you want. Then you use our simulation environment, which is in MATLAB or Python. And what you will get is the top video here. So this is, coverage control algorithm covering the lovely Georgia Tech logo. And you're going to modify it. You're going to do whatever you want. You're going to create your simulation files. When you're happy with what you see in the simulator, you upload what you have to the website through the user account that you've created. And then it'll get pushed to a Robotarium server. And what we do after that is actually validate this code. You'd be amazed how many people submit things that don't compile or run robots off the test bed or try to slam them into each other. And so once your experiment passes validation, if it doesn't, you'll get an email saying, hey, please fix this program you sent us. It'll actually get deployed onto the Robotarium. And so that's what the bottom video is. And after your experiment is over, any data you're interested in, the tracking data, the online robot data, any simulated states, you can save into a MAT or NumPy file that will get uploaded to the website through your user account, along with an overhead video like this. To get into a little more detail about the actual architecture, right? On the remote side, all you have access to is an email account, which will be giving you status updates about your experiments that have been submitted. Remote API simulator, MATLAB or Python again, and the web front end so that you actually get to interface with. And so your user code gets submitted through the web interface and then put into some lovely database. After the database, we have some simulation code validation, which is sent to our server. And then our server is running our own flavor of the same API. And so this allows us to actually command all the robots from a centralized point, which guarantees some safety for us. Gives us some virtualization techniques. So if you want to put in fake obstacles, if you want to put labels or anything down on the test bed, we can pass that through to get projected down to the test bed. And we have a Vicon tracking system, which we allow you guys to have access to so that you can record your data or just get state updates from the robots that are perfect. So with that groundwork of what the Robotarium is, I want to talk about the development that we've had actually running it for a global community. And so when we opened to the world in 2017, you'll notice this video is a little different. We're using very tiny robots called the Gritspot. That's this robot on the right picture on the left side with the golden crown. So it leveraged the original software, hardware, and algorithms of the original tabletop test bed where we had people submit directly to us and we would run. And so we ran it just like any other test bed, except the experiments were coming in remotely. We would sit there, we would run the experiment, we would send back the data in an autonomous fashion. But there was always a human supervisor in the room. And so a problem with human supervision when you don't know what is being done, here are two videos early from the Robotarium. One's going to work, one's not. And I want you to try to figure out which one's which. It's the same experiment. Great, right? So the top one is working. They're doing some leader-follower formation control thing. The bottom one could have been formation control. And so unlike local test beds or competitions where there's a task involved and you know what it should be doing, we have no idea what nominal operation should be. So it's very hard to debug. Beyond that, we need to have users trust that we are not going to look at their code, right? We're not going to look at what they're trying to research. So we cannot, without their consent, go in and figure out what their code is trying to do. Nor do I think I could parse code and say, this is what the nominal operation is supposed to be. And so when errors like this occur, it's really difficult to determine the source of the error, right? This could be a hardware failure, a motor blew out, could be a tracking failure, one of them isn't being tracked anymore. Could be Wi-Fi has dropped out. There's infinitely many. It could also be a user submitted something that doesn't work. And so that's what it's supposed to do on the hardware as compared to simulation. And so we got away with this for a while. So here's our usage data from the opening in August of 2017 to current. And so since 2017, we have over 2,200 users from every continent except for Antarctica. We've run nearly 10,000 experiments. I really wanted to cross that threshold before coming here, but we've nearly run 10,000 experiments. And so in the beginning, you can see when we first opened, we're running less than 50. And you can manage that with a human in the room without using all of your time. Then when people started using this for ICRA and IROS or for their classes, you'll see we'll spike up to around 700, 750 experiments a month. And so at about 10 minutes per experiment, ideally, that's about 120 hours of operation per month. That doesn't count charging. That's hopefully if every robot came out perfectly every time, ran your experiment, went back, and continuously did this, right? So that's not sustainable with a human operator in the room. And so what we did was really work towards automations and refining the test beds so that it can run this. So some things that we've decided that are requirements for robotic cloud infrastructure. And again, these are the things that are more my opinion, but I love having discussions and fighting over them. The first is minimizing the need for human input to run the system. So you can actually keep up with demands like this. And that means you develop reliable hardware and software infrastructure. The second is maximizing the repeatability of the system and user trust in the systems. You can't give room to blame the robots. I'm sure we've all deployed a robotic experiment and been like, the robot's the wrong thing, I'm perfect, right? And so if you have a remote user, it's important that they trust that the system will do the same thing every time. Third, and one of the more important ones that we'll spend time on, is managing the trade-off between user access and hardware safety. Remember, I don't vet anyone using the test bed. And so what we really need to do is let users do as much as they can, but also not let them break the hardware. And the last one goes hand in hand with this, but this is minimizing the amount of hand holding when deploying experiments. You want that the code that's being submitted to be able to run on a different robotic platform. You don't want to have any hidden tricks underneath the hood that basically allow the experiments to be successful without the user's knowledge of things that you're putting in. So just a brief hardware recommendation for if you are developing custom hardware or modifying hardware for cloud robotic applications. One of the biggest things that we did was change from the GritSpot to the GritSpot X. And so some things that are very useful, your robots are going to break, right? So this has been running for about 3 years. The motors fail constantly. So making them easily and reliably reproducible and repairable is imperative. Also making sure that they are standardized across robots. You don't want, we're looking at a multi-agent case here, but having different robotic hardware gives you different results depending on which robot the remote user randomly got access to. Dealing with power draw. So to keep up with global demand, this thing autonomously charges itself, is power state aware, and it moves robots on and off the test bed as needed. And so being able to deal with power generation and being able to charge yourself is incredibly important. Interfacing over the air, this is more for a multi-agent perspective, but it's really hard to maintain a robot fleet. And so making sure that you can actually do it from a centralized server is extremely important. And finally, this one I put because I don't see it enough, is providing intuitive feedback for your developers. So when I look at my robots, I can of course print out a log file and I can see the charge status of my robots or the connectivity status. And then I have to go over to all of my robots and say, are you robot one? No. Are you robot one? We have to find the one that's a problem. The better way you can do this is just provide intuitive feedback. Put an LED on. Red is low, purple is medium, green is high. It's just something that we did that streamlined our maintenance. Liam kind of scooped me on this one, but I'm going to agree with him on solving software environment challenges. User scripts that are submitted when they don't really have skin in the game will damage or corrupt your software environment. They will change directories, they will delete things, they will leave files that are lingering around, that will corrupt future robotic experiments. On top of that, you have system level heterogeneity, and you need to make sure your cross-platform dependencies are the same, application level heterogeneity. So you need to make sure that your system development, your software development is modular and consistent. And so the way that we solve this, especially the first problem, is utilizing Docker. So containerize everything. These are essentially lightweight VMs if you haven't used them before. I put lightweight in quotes because you can make massive Docker containers if you would like. You guarantee correct dependencies here because you're basically deploying applications. But the real reason that we use it is you can redeploy containers anytime there's an error or if you have a new submission come in. So when you send something to the Robotarium, we boot up your brand new perfect Docker container, fresh software environment so that your code runs. And then whatever you did to the software environment, we don't care. We blow it away. Next submission comes in, we boot up a new Docker container for you to run. Next, I want to talk about user access versus hardware safety. So this is the big one that we've been concerned with because we have multiple robots and you can cause collisions and do some real damage with these. So if we let users do whatever they want, here's the worst case experiment, right? They're being told to form a circle and then someone says, drive in a straight line to the other side of the circle. And so boom, right? Japan submits this at 3 in the morning. I get an email that says, please pick up the robots. I pick them up. In this example, we ripped off 1 encoder and 2 IR sensors. So you can do some real damage with this. This costs money, this costs time. But of course, we have a tracking system, we have a simulation system, and we can easily say, okay, look, these circles define how close you're allowed to be. And so if you get too close, too bad. We kill your experiment, we send back and say, robots collided, figure it out. Which doesn't seem entirely fair, especially because a lot of research deployed on here doesn't really care about collision avoidance. So what we provide as an option for users to use is barrier certificates. And so what this is doing is this is an optimal control algorithm. And the essential idea is there's a user desired control command here, right? Drive straight through one another. They're still being told that by the system. What we're doing is trying to find the minimum difference between what the user wants us to do and what we can do that respects the safety constraints here. So those circles are safety constraints. No two robots can be in any one circle. And so what the system figures out from a centralized point of view is how to move every robot directly to the other side of the circle, while also not allowing them to enter anyone else's circle. For a little more detail on this, the nice thing about them is that they're minimally invasive. If you provide a completely safe control structure, they will never be put in here. You'll never have the barriers actually jump in. So the main idea here is that we're minimizing the difference between what the user wants us to do, here UD, and what is safe, right? And so if you provide something that's safe, U equals UD, nothing's going to get changed. The other nice thing is this is a constraint-based approach, and so you can add on additional constraints. The video here are robots that are driving using single integrators. So the single integrator command that's being provided to them is being projected onto the test bed. And so what we've also put in are walls. So you can't drive my robots off the walls to slam into parked robots, to slam into the actual rigid edge of the arena. And so you can see the barriers acting and shrinking these arrows, these single integrator dynamics, when they get close to another robot or when they get close to the wall. So a real quick kind of future where we're going next. So people are using this, and we have been successful in enabling anyone around the world to actually deploy their stuff onto ground robots. Ground robots are nice. There's a lot of things we kind of overlooked when we're using them. They're great and stable. If you tell them to stop moving or network communication stops, they stop. When we go to quads, if they stop getting communication or if they stop working, they turn into rocks. And that's a real problem. But we're getting to a point where we can actually deploy these. The two videos here are showing three-dimensional barrier certificates. So essentially, allowing these guys to operate near one another and guarantee they never slam into each other. The one on the right actually also shows a charging routine where they actually land on inductive chargers and can continuously operate over and over and over again. And finally, as Liam kind of pointed out, these cloud robotic and remote access test beds provide a really good opportunity for pushing education into hardware domain. And so what we've been working on recently is actually developing block programming interfaces to push it down even further so that you don't have to program everything in Python and in MATLAB in order to deploy something on real robots and learn about the sim to real gap in personal experience. And so with that, I'd like to thank you guys for your attention, and I'll take any questions or comments on the presentation. I also want to advertise quickly, we are getting close with the quads and we want to start doing alpha testing. So if anyone here or out there wants to try using the Robotarium quads, please reach out to me at this email and we'll get in touch, and you can help us push this thing forward to be at the same level that the ground robots are. Thanks.
Everyone else got a cool microphone. All right. Question about about your funding situation, actually. You mentioned education, multiple times. I imagine you could get a fair amount of funding for doing this thing from an educational standpoint. Have you been able to get funding from other standpoints besides education for doing this work, which admittedly I think is really cool, but
so
funding problem.
The original goal of this project, so it's a fun story. The original goal was research-based. We built this for researchers by researchers. And so the original funding was to create a research enabling test bed. So that's the ONR and NSF funding perspective. What we found, and this is a nice thing about remote access hardware, our user base wasn't entirely using it for research. We started having educators creep in and developing classes around it. And so that's why we've pivoted, and we've actually not received funding for educational purposes yet. We're pushing in that direction now because the user base, about a third of our use is for research, either for education, for classes or for just outreach module type things.
Does it cost anything for researchers to use the system?
No, so long the vetting process for the user accounts is essentially, are you from a big company trying to make money? In which case, our real concern there is we don't want them monopolizing the test bed.
Okay.
But no, absolutely free, academic or educational purposes. Take a shot.
Awesome. And you can do that because there's funding sources.
So because it's established and yeah, I mean, we the whole point of this originally was to democratize access to robotics. And so we don't want to put it behind a paywall because one of the barriers we're jumping is funding, right? People don't have the funding to establish research test beds like this. So if we put a funding layer in front of it, it might be lower, but we're not really helping the cause.
Okay, let's thank Sean again for the amazing talk. And we will be having a lunch break. Please come back at 2.
Well, I'm glad this computer works. My computer exploded on the way here, so I had this fresh one that I needed to set up. I was like, thank you. Oh, well, I can talk to Liam directly. Yeah, absolutely.
Not anymore. So, but I mean, you still must have fair amount.
I mean, so the way we have it right now is I have one undergraduate and a master's degree development. The undergraduate turns it on. You have a whole Slack. As you know, it's perfect. If something goes wrong with their thing, I've gotten it down to emails maybe once every week. Really? So there's a paper that we have that was
Hello, Professor Barry, can you hear me?
Hi, yes, can you hear me okay? Hello? Hello?
Do you have some slides that you want to try sharing before we get started?
No, I don't.
Oh, I'm not able to hear you.
Hold on. Can you hear me now?
No, I could hear you before.
Yeah.
Do you want to try saying something and we can test the audio?
Testing, testing, testing. You still can't hear me?
No. Sudeep, can you confirm if you're able to hear on the Zoom end?
Yeah, I can hear it through Zoom.
Okay, tell me what kind of slides you need for today's meeting.
Oh, I think she was asking if you had slides that you wanted to show as part of your talk, or like video or anything that you want to share your screen through Zoom, essentially.
Okay, during the talk I will, but the talk's not today, is it?
The intention was that it was today, yeah.
Wait a minute, because I thought I was on the schedule for August.
Oh, wait, try something now.
Was there a miscommunication by chance? I think
it's just working.
Yeah, I thought this was the prep meeting for the talk. I mean,
yay!
I can give a talk, but I thought this was the prep meeting for the talk.
Oh, I see.
That's okay. That's okay. Well, we're gonna make this work.
Okay.
Tell me, because I have talks I give all the time. Oh my God, I'm in my car. Let me get in the back seat and get a talk ready for you. I thought this was the prep meeting for the talk. Yep, give me just 1 second, okay? I'm gonna get the back. Hey, we're engineers. We innovate. We're gonna make it happen.
No worries, no worries.
More exciting this way.
Yeah. Tell me a little bit about your group.
Yeah, so I can just sort of give you the intro for the workshop. So the workshop is about sort of robot learning in the cloud. And we see 3 components to this sort of overall idea, which is sort of remote robotics. One is that there's this democratization piece, which is what we're hoping you can speak about, which is enabling access to robotics experiments and hardware for potentially undergrad students or people who don't have background in hardware. Another aspect is benchmarking. And so we had some benchmarking talks this morning talking about how do we compare methods more easily if we have shared hardware in a central location. Yeah. Is that sort of enough of an overview, or do you want more information? I think all of your work about democratization or undergrad robotics education would be really useful here.
Okay, all right, give me just a minute. I'm gonna get some slides. I am so sorry. I thought we picked a different date for this event, but okay.
No worries. I know you're super busy with the other conference this week too.
That is so fine. Oh my God, I don't know how I ended up with the wrong date for this. Okay. All right, that is not a problem. I'm going to get some slides ready. I apologize to everyone.
Actually, so we have another recorded talk, so we could play that one first and you could give a talk in half an hour if you want.
Sure.
Is that
you want me to give the talk at 2:30 then?
Well, if you'd like to give it now, that's fine, but it's whatever's easier for you.
Okay, let me give the talk at 2:30. How long do you want me to speak for?
About 20 minutes and then like 10 minutes for Q&A.
Okay, good. And then let me try to get somewhere so I'm not in my car. And I will be ready in 30 minutes.
Okay, see you soon.
All right, I'll log back in 30 minutes. Thank you.
Bye.
All right, bye-bye.
Okay, sorry for the confusion, attendees, but I think we can get started. So thanks hope you all had a great lunch break. Small change of plan. So we had 2 afternoon talks. One is Professor Berry, who you just saw, and the other one is Anka Dragan. And so she has a pre-recorded talk that we're going to play because she had some unforeseen circumstances, so she's not able to make it live for Q&A, but hopefully if you have some interesting questions, we could always talk to her later on. We're just going to swap the order of those 2 talks. And let me prepare on the talk. Mute this one. Yeah, you can do the intro.
So just a short introduction of Professor Anka. Anka is an associate professor in the EECS department at UC Berkeley, where she runs the Inter-ACT lab. Her research focuses on algorithms for human-computer interaction, which would allow robots to better coordinate with people and solve tasks that we actually want them to do.
Down, turn up. Oh. Turn off this one.
Principles to keep in mind as you're designing your experiment. So first, hi everybody, I'm Anka Dragan, and I wanted to share a little bit of an intro to experimental design with some principles to keep in mind as you're designing your experiment. So first, let's talk about what an experiment is in the first place. And to talk about that, I'll just mention that we think of experiments traditionally as being about people answering questions in medicine, for instance, about how people react to different treatments. And in robotics, we think of experimental design as mainly something that human robot interaction researchers do when they set up user studies to test the design of robots that are to be used with and around humans. But there are lessons there that we can learn from them about designing experiments in robotics more broadly, even when your questions are algorithmic questions that are not directly about studying people. So even when we have sort of traditional problems like reinforcement learning, motion planning, etc., there are things that we should be thinking about when we're setting up our experiment. And so right off the bat, let me just say, these are the 4 ingredients we technically think about when it comes to experimental design. We talk about treatments. These are going to be the different conditions that you're testing. Responses, which are the measures. And then you're going to have experimental units, which if you're dealing with people, those would be your subjects, your participants, and then an allocation method, which is also called a subject allocation or an assignment method. So for very quickly, as a few examples, if it'd be in a medical field, a very traditional experiment would be your conditions, your treatments are the drug and the placebo. You are measuring certain symptom progression in the disease. Those are going to be your responses or your measures. Then your patients are going to be the subjects or the experimental units. And then the assignment method assigns subjects to the conditions. And typically that's done by what we call a between subject design in this area, where each patient will either be given the drug or the placebo, but not both. And the way we'll decide on that is by randomization. So remember that between subjects, it's a term that comes up. Now, in a human-robot interaction setting, an example might be, we can generate the robot's motion to be feasible only, do its thing, avoid bumping into things, etc. Or we can use an optimizer and optimize cost, optimize reward, something like that. And what we might be interested here as a question is, how does that affect how comfortable people are when they're working side by side with the robot? If you're energy efficient, for instance, you might have people end up being much more comfortable. So your subjects are the participants coming in, and the way you might allocate them might be between subjects, or you might choose something called within subjects, where each user will end up working with the robot both in the feasible condition and in the optimal condition, so that you can kind of get a comparison. So there are pros and cons between these two, and we'll touch upon that briefly later as well. Now, when you're in a robotics, kind of pure robotics, so to say, domain, by the way, I don't think there are pure robotics, so I think everything's about people, but I'm biased. So if you have a question like, and I'm going to use here an example from when I wrote my first paper in robotics back in the day. So this was a question of, if I'm running a motion planner, a trajectory optimizer, I could do the traditional thing, which use a fixed goal configuration, or I can account for the fact that there are many different ways to reach for an object, many different configurations that will work, and maybe it's useful for the optimizer to know about that set of goals. And so you might want to look at the effect that using a goal set has on the final cost of the solutions, and that's all well and good. Now, here's what's interesting. What are the experimental units when you don't have participants coming in? What's the equivalent of that? And so here what we have to think about is, what are going to be what are we going to measure the cost when we run these algorithms on? And the answer for experimental units here is the motion planning problem instances. They are the ones that are going to be looking at the two algorithms and evaluating them in a sense of, they're going to be able to tell you what the cost ended up being for each algorithm. So experimental units don't have to be subjects. They can be things like problem instances when you're doing algorithmic work, and you have to decide on what those are, and you have to decide on an allocation. Usually you just do within subjects here. Now, kind of stepping back, these are the ingredients of your experiment, but you don't just come up with them, in one shot and then that's it. You actually go through an iterative process if you want to do a good job, and that process starts with what your variables are. There are two main kinds of variables. There are a few more, but this is just a 15-minute crash course, so we're not going to go into that. There's dependent variables, which are essentially just going to be your measures. And then the more interesting part is, what are the independent variables? So the independent variables are not the same as the conditions or the treatments. The independent variables give rise to the conditions or treatments as you change, as you manipulate that independent variable. So for instance, what you actually change is the type of goal, or the size of the goal set. That's your independent variable. And it gives rise to a treatment where the size is 1 and a treatment where the size is more, maybe things in between. So that's the actual variable you're changing. So it's not whether you're using algorithm 1 or algorithm 2. That's, technically that could be an independent variable, but it'd be a very cheating way to get at an independent variable. What you want to focus on, what you want to identify, is what it is that is changing between these algorithms. And then you can form your hypothesis, which your hypothesis is going to have to look like an independent variable has a particular effect on a dependent variable. Or sometimes they're directional, like it positively affects or negatively affects the dependent variable. And so examples are optimizing motion will increase user comfort, or including goal sets in planning leads to lower cost solution. Notice it's not, I have an algorithm and it's better than the other one. It's the effect that an independent variable has, or maybe you can say a goal set size positively affects costs. And the reason I'm making a big deal out of this is because a lot of times when I look at robotics papers, they read something like this, right? There's going to be my algorithm, the other algorithm. I test mine, I test the other one, mine is better, end of story. And I think what's missing here a lot of the times is really sitting down and thinking, what is it that we're manipulating? What is the independent variable, set of independent variables? What are we changing here when we go from the other algorithm to my algorithm? And I think that's really important because forming a hypothesis in this way, by really thinking about what is the thing that you're changing, is going to force you to really articulate what your idea is, what your key insight is, right? So instead of just saying, I'm making a thing and it's better, you're going to come up with essentially the thing that's actually changing between the things, which is almost going to act as a more generalizable idea that's going to live beyond your application to one specific instance of an algorithm, and we're going to get back to that later. So good experiment design is gonna really force you to sit back and reflect on, how could I articulate my idea? What is it that I'm proposing here? And then you're gonna conduct an experiment. You're gonna design an experiment to actually test that that thing that you're proposing is actually improving or seeing the effect that you're hypothesizing. So that brings us to this natural question, which is, how do you design a good experiment? How do you do this well? And the disclaimer here is, by the way, in my own work, I strayed away from my own advice that I'm going to give you here numerous times. I'm by no means perfect at this, but I do find it important for everyone to be aware of these issues and think about them and do, you know, as best of a job as can be done. So taking a few steps back, let me first share that this very basic thing about experiments, that they should ideally be controlled. You will have no problem doing that if you work with algorithms in the lab, but for more complex problems, the issues arise, and I want you to be aware of this. So when I say controlled, this has a very specific term in the experimental design literature. A controlled experiment is an experiment in which the experimenter is in charge of assigning experimental units to treatments. And that's to distinguish it from something called an observational study. So what's wrong with observational studies? Well, here's an example that I think is pretty indicative. So this is a famous example of an observational study gone wrong. It goes back it's back in the day, and it was about studying the effects of estrogen treatment applied post-menopause to women, and looking at the effect on their health outcomes. So a team ran an observational study tracking over 90,000 women for 8 years. They recorded whether the women were taking estrogen or not, and they measured their coronary heart disease and a few other health indicators. And their analysis revealed that that low coronary heart disease, cardiovascular disease, correlates to estrogen treatment. So the conclusion was that estrogen treatment is good. People should take it post-menopause. It's going to help with their heart. But there's a problem here. And it has to do with the fact that it's not a controlled study. The experimenter did not assign the experimental units, the women here, to the two treatments, right? The two conditions. So instead, women decided whether they want to take estrogen or not. And that introduces what we call a confound. Basically, different women, if you're the kind of woman who wants to take estrogen to maybe improve your health, you're the kind of health conscious person who probably also is likely to exercise and do a lot of other things that are good for the health. And so the effect of that could not be disentangled from the effect that giving estrogen has. And in fact, when they ran a controlled study, it showed the opposite. Estrogen actually had a negative treatment, negative effect. And maybe it was something like health consciousness that had such a positive effect that compensated for that. And it made it seem like the estrogen was helping. So this idea of confounds is really foundational to good experiment design. And this is the main thing you want to watch out for. You want to identify those independent variables, and you want to test your hypothesis by avoiding confounds. And running a controlled study and a controlled experiment is, the first step towards that. Now, what's a confound in general? A confounding variable is a variable whose effect cannot be distinguished from the effect of your independent variable or variables. So health consciousness in the observational study is a confound, right? Because from the data, we cannot distinguish whether the improvement in health outcomes came from the treatment or from, these other things that people are doing because they were health conscious. So in user studies, we might worry, for instance, about properties of the population that is getting these treatments. So we might end up with a confound that's experienced with robots. If in one condition we end up with a set of participants that are have much higher exposure to robots, and therefore they're more comfortable around it, that's going to affect the data. So that's going to be a confound. If we use a within subject design, then so by the way, experience with robots, this is the kind of thing that you can eliminate as a confound, even without identifying that it could be a confound, because you can make sure to randomize and have enough people and randomize. So that's a thing, and not quite the kind of problem that you're going to have to worry about when your population is really, motion planning problems, for instance. With user studies, though, we also worry about ordering effects. If we're doing within subject designs where people are doing the task in one condition and again in the other condition, then we might see them improve at the task, not because of what the robot is doing, but really because of they've gotten better at it. And we fix that by something called counterbalancing. So we make sure that we have half the participants in one order, the other half of the participants in the other order, and the generalization of that for more conditions. Okay, so experience with robots, ordering effects. Now, some confounds are not about the population. They're about differences between the methods you're testing that are not your independent variable. So they're extraneous differences. So for instance, in a test about feasible versus optimal motion, I might not be consistent in where I time the trajectories that get executed on the robot. And if optimal motion ends up kind of having slower motion, that might lead people to be comfortable because of that timing difference and not because of the inherent difference between the way that these motions were, the geometry was generated. And so that's the kind of thing that you have to think about ahead of time and control for explicitly. And you want to write in your paper that you thought about it and this is the way you've controlled for it. So that's an example of trajectory timing. There's also differences that creep in that are very, very common. And these happen regardless of whether you're dealing with people or not. So for instance, you're going to end up with algorithmic hyperparameters. So when you tune your hyperparameters, this might be obvious, but still some people don't do it. So when you tune your hyperparameters for your algorithm, but you don't for the baseline, then you've introduced a confound because you don't know whether the improvement you're seeing was just because of that tuning. And so it's not even enough to use the same hyperparameters, because if you use the same hyperparameters, but you tuned that set to be based on your algorithm performing well, then all of a sudden you still have a confound. And so you really want to ideally pick validation data and tune basically optimize the baseline and your algorithm separately, and do whatever, give each algorithm the best shot you can give it. So that's kind of a common thing. you might be able to also blind yourself to which algorithm you're tuning if they happen to have the same hyperparameters, so that you don't invest a lot of work and careful finessing and tuning of one. That your mileage might vary with that. It's really not very easy to do in a lot of situations. Okay, so another example is differences between algorithms that slip in that are not captured by independent variables. So coming back to this picture, your idea might be a way to improve the state representation. And you might say, oh my God, I improved the state representation. This is great. It really improves the dependent measure. But what if for whatever reason, this method that you were testing was a second order method, whereas the baseline that was using the old state representation was also a first order method? Well, you've introduced a confound with that. And this might happen more often than you might think, because for instance, it might be that there's something about that new state representation that gels particularly well with the second order method. Or more often than not, it happens because we come up with an algorithm and the state of the art is not just that one change away from our algorithm, it's 2 or 3 or even more changes away. And then if we close our eyes to these changes, then we run the risk of attributing the improvement to the wrong reason, and then science goes down the drain. Or if another thing we can do is we don't identify the reason, we just say, look, this algorithm is better than this other one, trust me, this experiment says so. And again, we kind of lose touch with science, because without understanding the why, we're not really providing a lot of insight into the problem. So, and it's hard to generalize that to other algorithms. So I think it's really important to identify the independent variables correctly. And the way we can think about this is by what we call a factorial design. So you're going to have your state of the art, and instead of just testing your state of the algorithm, which is a new state representation and the second order method, you're going to break it up into 2 independent variables, state representation being one, optimizer being the other one. And you're going to test the full 2x2 factorial here. And this is helpful because what might be happening underneath the hood is you might notice that you might find an advantage of this combined method relative to the state of the art. But underneath the hood, what might be happening is that this is really an advantage that comes from the second order aspect and not from the new state representation. And it could even be that your new state representation does not help at all. In fact, it could be that it actually hinders, but then the second order more than compensates for that. So you have to essentially be very careful about these factorials so that you don't end up accidentally deceiving the reader with your message. And now, as you get more independent variables, you end up with, the full factorials really blow up. And in those cases, you should either kind of take a step back and make sure that you really think all those independent variables are necessary, or at the very least make an informed decision about which cells of this full factorial you want to leave out and explain that to your reader. Okay, so besides avoiding confounds, an important property of an experiment is construct validity, which means that what you're measuring is actually what you want to measure. And this breaks all the time when we take IQ tests and we think of them as measures of intelligence, when we ask people to rate their comfort and we think of that as being the actual comfort that they're experiencing. When we use sum squared error on test data and we think of that as accuracy, but and we're not accounting for the fact that different types of mistakes actually cost differently, and we really need a much more nuanced measure there. Or when we look at the final solution of that comes out of the final cost that comes out of an optimizer without necessarily thinking about timing aspects and stuff like that. So another concept is external validity, which is really important. You want your conclusions to be generalizable, and so you have to set up your experiment to allow for that. And conversely, you want to only claim the scope that you're actually generalizing to, that's actually backed up by your experiment. So to do that, you want to make sure that your experimental units are sampled from the target population. Like, don't run a study on a 25-year-old wild male when you want to claim something about the general population. And remember, the experimental units in algorithmic settings are the problem instances. And so what you want to make sure is that they're representative of the kinds of problems that you want to say that change actually is helpful. So I kick myself every time I test something on a random MVP or on a randomly generated world, because real worlds will look different and I lose that external validity. So increasing generalizability means covering many types of experimental units. It also means something more subtle, which is, remember how we were talking about goal sets versus a fixed goal in my first paper? Well, in my paper, I manipulated that via two algorithms, right? I chose CHOMP, which was a baseline, and I added goal sets and it became goal set CHOMP. And my generalization was basically there. Like that was it. It was, goal sets help CHOMP. So I wish that I would have thought about actually applying this to different algorithms, to different optimizers, because the insight was actually much more general than the specific of CHOMP. So instead of ending up with, a new and improved version of CHOMP, which is now out of date, we could have come up with something that was, really goal sets. They're helpful whenever you have an optimization-based motion planner. And we could have gotten at that by really testing on a wide range of such optimizers, which is harder to do, but nonetheless. Okay, so these are the ingredients of an experiment. The key is really to figure out what your independent variables are and to make sure you can test your hypothesized effect of these independent variables cleanly, without confounds, and with an eye towards construct and external validity. And again, remember, formulating hypothesis in terms of independent variables will force you to clearly articulate your key idea, and then good experiment design enables you to actually test that idea. With that, thank you.
And now we are ready for Professor Berry's talk. Professor Berry, if you're there, would you like to share your screen?
Yes, can you hear me okay?
Yes, we can hear you.
Okay, how many people are in the audience?
Let's see, about 10. Here, let me turn the camera around.
Okay, 10. All right, because I have got to apologize. This has never in my life happened before. And hey, there's a first time for everything. Okay, I am now sharing my slides. Okay, can you see them?
Yep, that worked great.
Okay, let me know when you're ready for me to start.
Do you want to read your intro again?
Yep. I'll just give a brief introduction to Professor Carlota. Carlota is a professor of electrical and computer engineering at the Rose-Hulman Institute for Technology. Her research focuses on educational mobile robotics and enhanced human-robot interfaces. One of her recent projects used a mobile robot platform to remotely command a fleet of robots. Carlota is also an expert on recruitment and retention activities for underrepresented population in electrical and computer engineering, and is an organizer and judge for the first robotic competition. Professor, you may begin.
Okay, thank you. Thank you so much for that presentation. So first of all, I have to totally apologize for misunderstanding and misreading my calendar and thinking that today was a prep meeting for the presentation and not the actual presentation. But thank God, as a paired professor, we have plenty of presentations on our computer, and I was actually able to find one that I think aligns closely with the purpose of today's talk about bots in the cloud and democratization of robotics and how we can make that more accessible to a larger community. So I'm going to share a little bit about my journey, about why I feel that there is a need to have this more ubiquitous perspective of robotics and robotics education and research. And then I will show some examples of how I do that in my everyday life. So First, during the pandemic, I was on sabbatical, luckily, and I started to become a lot more active on social media, and I began to share more about what I did as a professor. And I quickly discovered that people were actually hungry to learn about robotics research, STEM, and things of the sort. So this video right here was the beginning of that journey for me. And this was Juneteenth of 2020 when I had the epiphany to start just sharing the ways that normal people can see robotics. Because when you meet people and you tell them you're an electrical engineer or robotics engineer, they're always curious and they're always like, oh my God, that's like rocket science. You must be really brilliant and I could never do that. I'm like, no, STEM is for everyone. Robotics is for everyone, because if we're going to design solutions to make the world a better place, then we all need to understand it, respect it, and be involved in that journey. So I want to share these two videos with you, but first I have to actually share my sound. So give me just a second. I forgot to turn that on. So I will share my sound and play the videos for you. Okay, so here's the first one.
So this Juneteenth, I am bringing my STEM to the streets. I'm taking my robotics and engineering out of the classroom and onto all platforms
Thumbs
in
up
order
if
to
you can hear the
diversify
video.
STEM by connecting
Thank
with
you.
all people in order to show the humble beginnings that Black people have come from to be Black and excellent. Happy Juneteenth.
And so then, because I always have to show my daughter in every presentation I do, these are her feet. And this is also a great way for me to show that even young people can do robotics with a little instruction.
So this Juneteenth,
Sorry, go on.
She's up all night to the sun. I'm up all night to get some. She's up all night for good fun. I'm up all night to get lucky. We're up all night to the sun. We're up all night to get some. We're up all night for good fun. We're up all night to get lucky. We're up all night to get lucky. We're up all night to get.
And one of the things I like to share with communities is the reason that robotics is a great way for diversifying STEM and opening up the community to more people is because it is multidisciplinary. So no matter where your entry point is or where your interest lies, there is some way to point to something on an autonomous system to get people excited and engaged, whether you're a computer scientist, an engineer, social psychologist, social robotics, informatics, human robot action. Just there's a lot of different ways for people to be engaged and to see the importance of robotics. And another reason we have to do this is because if you look at television or even in some science fiction novels, robotics is typically represented as this scary thing. If you think iRobot and movies like that, and people are like, I'm scared of the robot, the robot's coming to kill me, right? I've actually done workshops for young people before who told me, I don't want to learn to program a robot. I don't want to know how to learn how to use a robot. I'm scared of the robot. So we have to get people to have a respect for technology and not be afraid of it so that we can use it to make the world a better place. And when we do create these systems, people aren't afraid to use them.
She's up all night.
So a big part of this is, I like to say, I live my life to make my passion my purpose. And I cannot separate who I am as an academic, a researcher, or a citizen. So it all has to come together in order to do things to benefit the world. So this was actually me as a new professor trying to figure out how to make the intersection of these things, because a person is the product of their dreams. So dream great dreams and then try to live those dreams. That's Maya Angelou. And a big part of that is realizing that all engineers don't look the same. All roboticists and computer scientists don't look the same. And knowing that me as an undergraduate student, and then as a master's and PhD, and even as a working engineer at Ford Motor Company and Detroit Edison, I didn't see engineers that look like me. And so I had to say, I want to break the mold so that robotics is accessible to everyone. Because if we're not in the room where these systems and this technology is being used to create a solution for the world, then there's chances for bias to creep in, right? And so the way that I keep that from happening is I need to be in there and go, has anybody considered how this facial recognition system looks or works on darker skin colors. Has anyone considered with crash test dummies how you can test the car if all the crash test dummies are the size of an average white male? Or has anyone considered, right, how this AI works if you're using a chatbot that within a couple of days it learns to be racist or misogynistic? So if there are not diverse voices in those spaces to address and to ask those questions, then these are the types of things that happen. And this type of education actually has to start with students in either high school or college, right? Technical courses can no longer just teach coding or building electronics or breadboarding. They have to also inject who are you as a world citizen and who will you be as a technologist. So one of the first things that I always show are these slides, because I want to talk about hashtag I look like an engineer. I look like a scientist. How can we make this technology look like the world that we live in, so that when we think about an engineer, or when I Google an engineer online, or when I search for it, or even when I'm walking around my engineering building, are the pictures on the wall pictures of people that look like this? Or are they pictures of people who all look the same? Okay, so that's one of the ways that we democratize this technology. So I do this with robotics education that then transitions into robotics research and transitions into robotics outreach. And I will talk a little bit about how I do that. But here's where my beginning was. So before I became active on social media, before I began doing all of these presentations, this was just me in my classroom. Before I had the epiphany that why should these students be the only ones to benefit from my knowledge, right? Because the things that I have to give to make the world a better place can not only be shown to these students. A big part of this is scaffolding, though. Bloom's taxonomy, you start with define and you work your way up to synthesis. So if I am doing a workshop for a 9-year-old about robotics, I'm not going to tell them the same thing that I'm going to tell a high school graduate, an undergraduate student, or a grad student. But that doesn't mean that everyone cannot benefit to this knowledge on some level. Like that video that I just showed you with my daughter. I don't talk to her about Bratenberg vehicles or about control architectures or artificial intelligence. All she knows is we don't want the robot to hit anything. That's potential field navigation, that's obstacle avoidance. So she's learning these things. And as she progresses up the level, she's learning more about this technology. And then she will actually be there and be able to do those things that she has seen because she has established some familiarity. And obviously, because I'm her mom, that means eventually when she did Vex Robotics and she did first Lego League and she did these things with her Girl Scouts, and they're now teaching young people about robotics. So now I'm creating after my own. That's part of that. To him, whom much is given, much is required. I take this knowledge and I don't just keep it, but I then download it into those future generations so that we then have a whole generation of people who can walk around and can seamlessly talk about coding and talk about technologies and talk about sensors. And for them, these things are not foreign and they're able to do it. So my epiphany was you take this out of the classroom. And so this is what this looks like when I take this out of the classroom. This is me mentoring my daughter's robotics team. This is me doing robotics road shows with Create Robots, which are like iRobots, and going and speaking at libraries to children about robotics. And of course, doing the first robotics competition, being a judge advisor, and also bringing the competition to my university. And then while they're there, have those high school kids who are excited about competing with their robot walk around and go to the Maker Lab and go to the Department of Electrical Engineering and look at the types of labs that they will do if they choose engineering as a career. So this is how you take the robotics out of the classroom and look at this intersectional nature of who I am as a roboticist, as an engineer, as a professor. And I bring all this intersectionality again together in something that I call a noir STEMinist. I can't think of a word to define it. I am a STEMinist, but it's more than about being a STEMinist. It's also about being more brown and Black people and people who are historically marginalized and minoritized and who you don't normally see in this field together. So I like to say it's about bringing robotics and STEM people and bringing people to robotics and STEM to educate and diversify the profession, or in very simple terms, my STEM is for the streets. And so part of that is educating people about how important it is for them to be there, but also making sure they understand that this has not been a crystal stair and that it is not just a leaky pipeline, because it's not just a pipe. There's not one way in, there's not one way out, and the water just does not freely flow. You don't wake up one day and say, I want to be an engineer, and you just flow out the other side unless there's holes in the pipeline. It's really more of an obstacle course. And along that obstacle course, there may be some alligators, there may be some moats, there may be some daggers and some arrows. And part of my job is to make people aware of that and to give them the resources they need to be successful. That includes education and knowing, finding a community and a support network for things that you need to do that, knowing about resources you need, such as if you're a college student, going to get tutored, going to get a study guide, going to office hours, reading the syllabus, what is the rubric for this assignment, making sure that you're doing that. And I honestly just wanted to be a high school math teacher when my journey started. And because I was good at math and science, someone told me I should be an engineer. And I said, what is an engineer? So part of knowing your resources is understanding and educating yourself on the field that you've chosen to study. I teach a lot of freshmen who show up their freshman year and can't tell me what an engineer is, but have decided to major in it. It is extremely important that you go. We have YouTube and Google at our fingertips now. What do engineers do? What is a robot? What does a roboticist do? What does a computer science do? So being educated about your journey so that you can get there, and knowing that there are a lot of things that may happen, but if this is what you purpose in your mind to do, it is absolutely possible for you to do that. So I had to first get rid of that Black woman superhero complex, right? And part of that is I don't see a lot of people who look like me. I don't see any role models who look like me. It can't be lonely, but I have to recognize it can be done. So find strength in your weakness. Know that imposter syndrome is real. Realize you need help and get it. Be dedicated, focused, and disciplined. Sometimes you have to run faster and jump higher, but you do it and you do it without complaint. Be the change you seek and make sure you're doing what you enjoy that is passionate so that you can do that without challenges, and know that self-care is important and when you need to take breaks. So one of the things I did when I first got to my tenure track position was I started a scholarship program. I didn't see a lot of Black and brown students who were coming into my university who were completely knowledgeable or had the hands-on experience they needed to be successful in engineering. So they needed to do more physics, they needed to do more calculus. So I started a scholarship program with mentoring, community building, and networking, and workshops and scholarships. And so here's a video about some of the things that we do with these young people in the summertime so that when they arrive, they are ready to go and hit the ground running.
This is the Rosebud Spark Design Competition. And it's really to introduce the high school students to the design process into engineering.
We get high school students, team them up together, sometimes with college students. Each part of the competition requires them to either maybe tinker with a printed circuit board, maybe they need to write a little bit of code, maybe they need to wire things together.
Microbit kits were donated from Spark Fund. So a microbit is like a little microcontroller or a baby computer, and they're building an electronic circuit and they're programming it with this software. And so the final design challenge is they have to design some kind of game using the electronics and all the tools that they have on their table.
The hope is they learn something about computer science, and they also get a sense of what Rose-Hulman is, what type of school we are, what type of projects we do here.
So we decided to do like a pinball setup. So it's thrown up and then there are different like obstacles that will make sounds when it's hit and the lights will go off. And we also have the flickers so that you can keep the ball in motion, and there's a little goalpost for when it actually falls through.
And this is probably some of the best engineering hands-on experience you can get. Prior to going into college, I was just kind of forced into it as far as, oh, you like math and science, engineering is a good fit. Okay, engineering sounds like it's a good fit. So when you get the hands-on experience of you get a design problem and you actually have to make it, you get to see that engineering design process and you get a taste for what that's like before you have to make that decision of what you want to study in school.
When I was younger, my thing was Legos. Now you get to do it with microcontrollers and lights and buzzers and turning things on and making things spark and fly and all of that. Learning that you can create something with your own hands and you don't need an adult to help you to write a program or to help you build a circuit. You could do it all yourself. It's pretty cool.
And so what I hope you see there is that there's a diversity of young people engaging in
STEM, but I also want you to see that the success happens when they go on to graduate. So the young lady who was interviewed in that video actually graduated about 2 months ago, and she graduated as the president of the National Society of Black Engineers. And so when these young people not only go on to do this type of STEM work, but go on to be leaders in their community and to be engineers for working, then we know that we are opening up the gateways to make this more accessible to more people. And so that's when I know I have had that success. And like I said, robotics is great for this because of the multidisciplinary connections here. This slide is actually a little older because I've now updated it, because we used to say a robot is a mechanical system that has a brain or controller that is given intelligence through software and an artificial intelligence that uses electronics for sensing, because robotics control architectures are sense, then plan, then act. So electronic software and mechanical systems can do that. But we now also talk about robotics also has, assistive technologies, automation. So biomedical engineers can do robotics. Psychologists and sociologists can do robotics if you think about it from a perspective of human-robot interaction. And these multidisciplinary connections are what make it so exciting, because even as a student or a professor, I no longer can just say I'm an electrical and controls engineer and this is my little box and where I live. I have to be able to make connections to these people in these other disciplines, and I have to also be able to speak to them about this thing that I've designed in a way such their knowledge, their depth and breadth of knowledge can then intersect with mine so that we can make this compelling system. And so this draws students from all these disciplines together, and the benefits of it are the divergent interests, the different prerequisites, different people. I may be good at coding, someone else may be good at electronics, someone else may be good at CADing or designing robot chassis or doing 3D printing. But when we all come together, we can make this really powerful system here. So now we're saying that looking at this diversity in robotics is not just about racial or ethnic or socioeconomic, but it's also about diversity in skill set, diversity in ability, diversity in thought. And all of these things have to come together to make this powerful system. So here's another example of how we do this in engineering when we bring students together as freshmen and have them learn basic electronics and then use that in order to design robotic systems.
Welcome to the Monster Mash.
And then we continue to scaffold that knowledge, because one of the main things you will hear from students is that they don't understand how calculus, chemistry, physics, and their technical communications courses affect what they want to do for the rest of their life, like engineering. Why are you making me take all these humanities classes? Why are you making me read these books? And so we not only talk to them about ethics, but that it's important that you're able to document your ideas by doing technical communications and technical presentations so that you can sell people on your ideas so that they want to build them or give you money to do your cool projects. So you do that from their freshman year on, and then in their senior year, as one of the co-directors of the robotics minor, we have a multidisciplinary robotics minor. Our students take mobile robotics as well as robotics engineering. So now you start to marry those classes together by having them implement things like artificial intelligence on a robot by using A-star or D-star search to do mapping, localization, path planning, etc. So here's an example where students had to design a human-robot interface to remotely control a robot. They could develop it in processing in Java and MATLAB, etc., and then use that to map the world.
Hello, Dr. Berry, and welcome to our mapping video. Before me, you see the GUI, which right now has assumed that every single cell is an obstacle. As the robot moves through, it's going to update saying this is not an obstacle, and these are where the robot is seeing walls from the IR readings. So you're going to see the robot turn a lot. It likes to read in this orientation. We have a custom send format that we're looking for, so we kind of need the robot in that position. So you're going to see the robot move a lot just to line up like this in each cell so these values are correct. Garrett, would you like to explain the robot and how
Basically, we are starting in the bottom left corner or 3, 0 in your standings, 3 in our standings. So basically, the robot's going to move through autonomously.
I feel like we're in the corner right now, so it's kind of cool because the way we've set it up is live. Plus, you know, we have a whole new world because we're showing you a whole new world. So before we look at the final GUI, we're going to be looking for 2 full obstacles and then a wall in between, and we'll also be picking up the eye readings from all the side walls. And so that is what we can see here. 5 and 9 and 7 and 11 are full obstacles.
So by showing students that there's a practical application to the work that they're doing, it gives it more meaning, right? So I'm not just giving them assignments for them to do them, but also to show them how you would need this stuff. So if we're talking about search and rescue robotics, and you want a robot that is able to go into an unknown world, try to figure out where it is if you've given it the map in advance. Then either it maps its own world or figure out where it is, and then has to go find something in that world. So here's another example of how we do that, where we now have a robot that has been kidnapped and is now lost in the world, and it needs to somehow figure out where it is in that world and then move from point A to point B, maybe to go retrieve something and return it to an exit.
Okay, so this is localization. So for the map of the world, we've translated it to our cell numbers. So we are starting in 3, 2, and we're gonna find out where we are once we end in 0, 2. In our sense, this is 11 and 8. What you're gonna see over here as the robot's moving is this is gonna say this is where we think we are. And then once it settles into one location where it knows it is, it's gonna update our GUI with graphics.
You want to start, Kira?
So we now think we were in 3 or 11.
You see the numbers at the bottom.
We now think we're either in 1, 2, 9, or 10. Same thing. We finish in
And
0,
boom.
2. We are currently right there, and that is where we started.
So that young lady is also now a working computer engineer. So human-robot interaction is compelling because it's a field that intersects all these things, because it's a field of study where you understand, design, and evaluate robotic systems. And you look at principles to have them effectively communicate with and used by people. But now we have the issue that when you actually integrate humans into the loop, you do have to consider how robotics is going to affect those people, how those people are going to perceive those things. There have been some examples recently on social media that have shown some robots that were a little bit too human-like, and they kind of fell off in the uncanny valley where people become a little bit uncomfortable with them. So then you have to think about things like how anthropomorphized or how human-looking a robot should be for people to be comfortable using it. And then another example recently has been entertainment robotics, where you look at ways to actually design robotic systems that will entertain users. I'll show a little bit of this, where I had students actually create a robot that was going to play music, that's going to entertain children or adults. But robotics can hit on many different aspects of our life. One big entertainment robot was the Sony Idol at one point. And then, as I recently mentioned, urban search and rescue would be another place where you could show students the importance and relevance of the work that they're doing. As shown here, where I have simulated there are Mario and Luigi are on a train track, and you don't want them to be run over by the train. So this robot has now gone on the train track to identify them and take them off before anything could hurt them. Right, and so I can do this one, and for the students, help them to understand the importance and so the robot has detected there was somebody on the track and is stopping to get them off if we're continuing along its path to make sure that the field is clear for the train to they travel. And so artificial intelligence is a great way to give a robot the intelligence that it needs to be able to do these things like we've shown here, such as having an internal model of the world, problem solving, knowledge representation, planning and reasoning, and search. So this image here is about a sensory ecosphere. It is actually an image from my dissertation, which I completed probably almost 20 years ago now. And it is a way of representing the robot in the center, its ego, and all of the knowledge it has about its world, whether it is objects, whether it's sensor data, the important things, so that you can now put this inside of a human robot interface so that you have a compact way of representing what the robot thinks and knows. The way I do this with my students now is I have them use LEDs. They put colored LEDs on their robot, and the color should change by whether the robot is randomly wandering, if it's doing obstacle detection, whether it's path planning, localizing, mapping, etc. And by having a way to represent the robot's intelligence, you can see if it's actively completing the task, if it's solving the problem, if it has represented knowledge correctly, and with this information. As a human user, I can either step into help, I can share it or trade it, control, or if the robot's doing great, I can continue with autonomous control, or I could take over and do remote control or teleoperation. And so the reason all of these things are so important, as I mentioned earlier, is because when they don't exist and we don't have this democratized way of looking at robotics where everyone is involved in the process, that is where bias can creep in. Here's an example that was on Twitter last year, where they had developed an algorithm for fixing highly pixelated images. And when you would upload them, no matter what the image looked like, including Barack Obama, they turned it into a white male. And so this is an example of things that happen when you do not have a rich data set and you don't have people in the room who speak to, do we have enough of all different types of images to test this algorithm on? Or are we doing some kind of filter on it? And if there's mostly white males. Amazon also had an example recently where they were using AI to pick out resumes for jobs and found that it was basically filtering out most of the women, because it was using the model for the current technology staff in order to determine the resumes to pull. And since it was mostly men, that was another example of where bias shows up when the things that are training the AI are not diverse enough. There's another example that was on social media where this machine was designed as a soap dispenser, but it did not recognize
Futurism.
dark skin.
Come to your honey. Too black?
Too black.
Yeah.
What I'll
Come
do,
again. Come again, Sashi. No. You too back. Move away.
What I can do, they get.
What you have to do
is how racial this thing is.
Yeah.
I have to use that piece of white. Let's say a napkin and show it. So what's the difference?
And so I won't show this, but another example recently that has been highlighted is in machine learning and artificial intelligence has been the documentary by Joy Bulamwini called Coded Bias, where we found that facial recognition systems did not recognize brown and black faces, and she had to wear a white face mask to do her research. So I would highly encourage people to go and watch that one on social media or YouTube as well. So we know that bias in robotics and bias in every part of society is everywhere, and it can creep in through assumptions, model priors, and how do we address and recognize these things, and how do we fix them? Because when we don't fix them, they can lead to injustice. Some examples of this are those facial recognition systems have been shown to be used by some police departments with a grainy image and a driver's license photo to arrest people. So this guy was arrested, Robert Williams, for shoplifting. And obviously it was not him, but they used that grainy photo and his driver's license image to decide that it was him. And there have been at least 2 cases of this in the last year where, of course, these people were eventually vindicated, but they are now suing the police department because we cannot use AI in criminal justice if we cannot know that our AI is biased and cannot be trusted to make important decisions like deciding about someone's freedom. So strategies for addressing this bias is developers must consider ethical implications of robotics usage. Educators must include ethics and societal questions in training. Teams must be diverse to provide unique perspectives and solutions, and researchers must reference the work of diverse roboticists who do sometimes have these perspectives, but their work has to be cited to do that. Because of that, Black in Robotics now has a reading list, which you can find online. And there are also organizations like cipher.org to make sure that you are referencing some of these diverse communities. It is important to actively promote diversity in developing teams in academia, ensure that bias is considered in the research and application of robotic systems, and make bias training and its effective robotic applications and methods for mitigating harm a component of any type of STEM curriculum. So the organizations that I represent today, other than my company, Noir STEMinist, are Black in Robotics, which has a mission to improve community accountability and advocacy with networking, mentorship, social media presence, showcasing and normalizing Black excellence in robotics, connecting academia and industry for diverse talent, supporting and defending equity in performance and ethical issues, and being a conduit for all roboticists to participate in solutions, identifying best practices, and holding each other accountable for equitable designs. I also represent, I'm a co-founder for Black in Robotics, which is a call to action for creating anti-racist institutions and completes our work through messaging, policy, education awareness, a social media campaign, community engagement, connecting with allies, strategic planning, as well as finance. I encourage you to visit both of these websites and also to visit them on social media to learn more about the work that they're doing. So in conclusion, robotics is great for recruiting diverse populations to STEM. It's great not only just for education, but for outreach and for research. And you cannot separate these things. They all have to inform each other because they have to be interconnected and they have to be married together. Robotics is ideal for showing connections between multiple disciplines and for bringing diverse communities together, and is a great tool for educating and enticing future scholars to transmit, transform, and extend knowledge. Robotics, AI, deep learning, machine learning, natural language processing, all of them can suffer from bias, just as people can. But the thing that is important is to be aware of it and have strategies in place to address it, and that these problems can't be solved with diverse teams, awareness, and education. And with that, I'm done, and I will end with these final thoughts. I've learned that people will forget what you said, people will forget what you did, but people will never forget how you made them feel. And you are alone or enough, and you don't have anything to prove to anyone. So authenticity is key and important. I'm ready to receive questions, but I highly encourage everyone to follow me on social media, and as well as my YouTube channel, to see some more ways that I use those platforms to educate others about robotics in order to diversify the field. And thank you for having me.
Thanks, Professor Berry, for the great talk. I can attest to the fact that her Twitter content is great, so I would highly recommend following her there. I think we have time for a few questions. I'm going to start with one. I can imagine that you could classify robotics education into two sort of categories. So one category is a system that's designed specifically for education. So like I would put first robotics in this category, and like a lot of the workshops that you've done, that kind of thing. And then maybe another category is we take real world robotics applications or research and make it more accessible to younger students.
Absolutely.
Like one example I would put there is like one of our speakers earlier was talking about a recycling application, which is very industrially grounded, but obviously that would be much messier to put that into like a course or a workshop for K-12 students. So I'm curious, how do you know which of these categories you should be designing for?
I think they're both important. And I think any entry point for students is exciting, right? That second one you mentioned is big in problem-based learning. Problem-based learning can sometimes be a bit difficult for novices, right? So I think if I'm looking at someone who's starting on their STEM journey, first robotics, first Lego League, Bot Ball, Vex Robotics, Sea Perch, I think those are all great because a lot of times kids are going to need a little bit more guidance, a little bit more scaffolding because they don't really know coding yet. They may not know a lot about, motors and actuators, etc. So that's probably a good starting point. Then once they're in their journey a bit, giving them a few more problem-based type activities that relevance, like in my first fixed robotics team, they always had a project affiliated with the team. So there was a basic challenge they have to do, and then there was also an additional project. So that was kind of marrying the two things together. Here's STEM for STEM's sake because I want you to do it, but then here is something that you can do, a real world application to give you that relevance. So especially once you get to your collegiate journey, I think giving those real world applications, it's not just in robotics, but in everything. So when I'm teaching my students circuits even, this is why you needed integrals. This is why you needed differential equations. This is why you learned that stuff that you hated at the time, right? Because I need you to be able to solve a system of equations to solve voltage, current, and power. So I think that's where you do that. But always knowing where the knowledge level is of the students that you're trying to connect with or the people you're trying to connect with. Like some things I have on my social media, robotic slam poetry, honey. That's where I marry my art and my STEM together. And I'm assuming the people who are watching our robotic slam poetry videos, they know nothing, right? But they can relate to poetry, they can relate to singing and hip hop music. So if I'm thinking about, hey, here's my robot that can detect light, this is a photoresistor, it's used as a sensor. I just snuck a little bit of technology into something that they weren't expecting to see.
Great, thanks. Any other questions?
Thanks. Great talk. I have a question. So a lot of this, what you've shown is students really getting interest because they get hands-on, right? They're building the robots, they're watching it slam into walls when it messes up or do the right thing, right? Since this workshop has to do with the cloud, what do you think the same impact can be had if students don't have direct access to the robots, right? If you had a system that they can remote into, is it going to be as engaging? Is it a direction that we should go down? You know, is that something? Do you have any experience in it, or do you have any opinions on it?
I do. I actually have some personal experience. So as I was an undergraduate student at Georgia Tech, in my first robotics course, they had physical robots. Only the PhD and master students and TAs could use the robot because there were concerns it was so expensive, it could be broken, etc. So they would let us write the software or simulate, but we couldn't actually touch the robot. That's one reason why in all my workshops and in all my robotics courses, I do give some kind of kit or some kind of hands-on robot because I think there are some benefits. I will tell you about the benefits and then I will talk to you about if you don't have that. I still think it's important to do it. So some of the benefits in using a physical system is that if you're a CS student, for example, you could write the biggest code in the world and it can run beautifully, but then try to download it to a microcontroller that has memory issues. Or if you're remotely controlling a robot, you have to think about bandwidth issues. Like the robot has just detected an obstacle, but it's still moving so that by the time that data gets back to your software wirelessly, the robot's not there anymore. So it's now hitting the wall, like you just said. So there's a lot of benefit in being able to connect the theory of controls or computer or coding with a physical system to deal with things like dead reckoning or odometry error or sensor error, etc. But let's say you don't have the resources to do that. So Back in Robotics actually does workshops on Zoom virtually, and we will ship kits to people's homes to help them to do that. But there's some great simulators right now. Tinkercad, I cannot emphasize enough. Tinkercad can be used to simulate motors, building things on a breadboard. There's another website called Dawson Virtual Lab where you write Arduino code on the website and then you see the robot actually implement that code and you can do wall following, obstacle avoidance, motion control. So even simulators teach you algorithmic thinking. It teaches you how to break down a problem into a software system. I have my students do that for their pre-labs before they do anything on the robot. They make a software development plan and it teaches them a systematic approach to solving a problem. Like designing a robot to exit out of a map or to map a world or to avoid an obstacle or to drive in a circle or whatever that may be. So yes, there are lots of benefits to having virtual or simulated knowledge, and YouTube is a big one, a great one, I might add. But then also just going online and going and finding some really cheap hobbyist kits at some point would be great too. Elegoo has some stuff. Arduino Spark Fun Education has some relatively cheap kits. Just to get some things in people's hands because that hands-on and minds-on
active learning engagement, when you bring all that together, there's some benefit there as well.
Great. Let's thank Professor Berry again for her time and for her great talk.
Thank you for having me. And once again, I apologize for getting the dates wrong. I did just get back in town and released a book today, which I did not mention that. Another way of marrying art with STEM to get people excited is I just wrote a STEM romance novel as a way of normalizing seeing women doing STEM and living their everyday life. So Elevated Inferno, it is available on Amazon today.
Great. Thank you, Professor Berry. We're going to have a 15-minute break and then we will regroup for our panel.
Thank you, Victoria, for having me.
Bye.
Bye-bye.
Okay, let's go ahead and get started. This is going to be a fairly informal panel based on the relative size of speakers and audience. So I would invite all of the audience members to come on down here.
Yeah.
Oh yeah.
Yeah.
Feel free to scooch. Okay. We do have a camera view here. Here, yeah, I can carry. Do you want to go in between me and Laryl, and I can come over here, just so all the speakers are together. Okay, I think everyone's somewhat visible. Great. So I'm one of the organizers, Victoria. I'm going to moderate this panel. So to kick us off, we'll have you all just say your name again so people know who you are. And as a little starter question, you can also answer what percentage of the time do you currently perform remote versus in-person experiments? And I'll just pass this down.
Hey, I'm back, Charlie from Worcester Polytechnic Institute. I spent 0 hours using remote setups for now. Happy to discuss.
Hey all, I'm Laryl. I'm from NYU and like Beck. Am I saying it right?
Beck, yeah.
Beck, yeah. I spend 0% of my time doing any remote experiments.
My name is Sean Wilson from Georgia Tech. And so I split my life between academic and applied world. I work at GTRI as well. So on the GTRI side of things, I do 0% remote. On the academic side of things, it's nearing 100% because it's just really easy once you can just hit a button and send away your experiment.
I'm Colleen from DeepMind. Depends how you count remote, but pretty much 100% if it's the floor down and I don't go there. Just go to take an object out of the gripper if it gets stuck.
Great. Well, it sounds like this is basically a debate. We've got our 0% remote team on this side and our 100% remote team on that side. So the next question is, what are your dream desiderata for a remote robotics benchmark? Like what features would be most important for you? I'm especially interested for the people who are currently 0% remote.
So this is pretty far-fetched, but it would be pretty cool to have like a cloud benchmark for continual learning. Because then I feel like if you do a continual learning experiment in your lab, it's hard to prove that it was a continual learning experiment, that you didn't go fix it. But if it's in the cloud, it's standardized. Everyone has the same initial state, and then everyone sends their learning algorithm, and you come back like 2 weeks later and you see where everyone has landed.
I'll turn it on its head a bit because I don't have one. I want to get to the point where we can actually start arguing about what the benchmark is. So have communities start yelling and saying, no, mine's the best if we look at this metric, and mine's the best if we look at this metric, and not mine's the best on this hardware and this setup in my lab that you can't touch, and yours maybe is better there. And I don't know. So that's my take on it, I guess.
Yeah, I also agree with Sean. Yeah, I think one of the issues is that because I don't use it, I think I need to first use a remote benchmark to see what goes wrong with it. But in general, I think having a setup that is easy to use, I think is very important, right? If you think about how other fields operate, it's so easy to, download a benchmark and use it. If something was easy to use, I think that would trump things like, is it actually, the right thing to do or not sometimes, right? As long as it's easy to do, we can get started with something and we can keep improving it until it becomes the right thing to do.
So reset mechanisms would have been awesome to have. I work on robotic manipulation, so it's quite tough to come up with reset mechanisms. I would love to, for example, have a non-contact setup. That would be the dream. But all these things that you do to avoid contact, we have to make contact all the time. But there are very creative solutions to that too, right? For example, in your setup, you are making these like surfaces. That's what I mean. I guess that also has been used, like that kind of setup has been used for several learning papers that I have been seeing. That's great, but I must also say I do not consider myself as a robot learning person. I consider myself more like a robotics, like in a more general sense. Like learning is just one of the options, and within that option, I also want to have like mechanism design aspect inside the picture, or sometimes even like I want to just like program something very simple and see what it does. Have maybe more conventional algorithm and see what it does. So when we have a remote setup, I think in these days it is more geared towards learning community, as far as I like. This is my impression. So that doesn't work with me that well either. But yeah.
So I've got a follow-up question on that. It does seem like we have somewhat disparate benchmarks for the learning community versus maybe more planning type things. And obviously you've worked on a lot of benchmarks in the past. I'm curious to see how much learning community engagement you've gotten on those benchmarks and whether it's possible to unite these areas.
Yeah, I think we speak different languages and I don't understand why. What I'm trying to say, it doesn't have to be that way. For example, I mean, this is the same world we are talking about. It doesn't have to be geared towards a particular community, right? There's a task. There are some performance metrics. There are some constraints on it. There are some parameters that we change within that task. And there's a robot. Whatever you do in between is, to me, not very relevant from a benchmarking perspective.
Thanks. Yeah, I think that makes a lot of sense. I wonder if part of the issue we have with the like learning, not learning, all these things is that often these methods kind of assume slightly different sets of inputs and different outputs. And so then you can kind of make a task impossible from one method or from another based on what kind of sensors you allow, what kind of information about the space or objects you assume are given to you. And so if we want to have a benchmark that's accessible to like all these different approaches, we'd have to think carefully about what the assumptions we make for the method are and how much space we can give to different approaches.
I think that's exactly the discussion we should have. Like, I mean, why don't we have these discussions beforehand, right? Like, because ideally we have same assumptions because we are trying to solve same problems, isn't it?
Sometimes we are and sometimes we aren't, I guess. Like if you're doing an industrial warehouse setting, you have access to some things. If you're doing self-driving cars outside in the wild, you have access to different things. I don't know if someone else wants to comment.
Yeah, so this is sort of add on to what Colleen said, right? Like it depends upon what do you actually care about, right? So in some cases you may care about, let's say, generalization. That is, I want to see how this method works when I change the inputs, versus in some cases I care about, okay, everything is known in the world, how do I solve it over there? And some algorithms are just geared towards solving some of these problems better and some other methods, right? So I think that sort of interaction is also important to sort of note. But I also agree that in general, when we create a benchmark, we should try to have a setup that is amenable to any solution. Because even if you say, okay, I want to create a robot learning benchmark, it should be something that even something which is not learning may be able to solve it. Because in a lot of cases that we have seen, even doing something purely open loop could work, or even like some very weak heuristic could also work, right? And we need to have the scope to actually try those out as well.
So I'll just give one example. Some of these benchmarks might assume that the user has access to ground truth state information about the object or something like that. And some might just give you a visual observation. It seems pretty clear that if you assume access to state, the problem is going to be easier to solve. So how can we reconcile these two sort of camps of methods into one benchmark?
Well, so just being a learning person, I would say that if you want to, let's say, use a planner, you need to do your own state estimation, right? So if you have images, do state estimation, try to figure that out, and then use your planner. You cannot just be like, oh, I have a planner and I'm going to use it, but I need states. Right? So I think it will also force like other sort of approaches to look at the problem in a more holistic way, maybe. Yes.
I mean, from a scientific looking discipline, I mean, ground truth needs to be in there somewhere, right? If you want to say something about the performance of your path planner, you should know what the real robot did. You shouldn't have just what you think it did. So that information should be in there anyway, and potentially part of the benchmark, right? How did it do really, not how did it think it did, right? If it slams into a wall and says, no, I made it to the door, we're fine. That's not necessarily a good solution.
So to clarify, are you saying we need ground truth access to some reward or more than that?
I think you need it to the reward and also for the performance metric, right? To see how well has it done really. So I mean, you can limit what the input is, right? And then you can compare them based on what their inputs to the reward function or to the actual machine learning algorithm is. But you will always need that ground truth state, I think. Feel free to argue.
Well, I think it's kind of unsolved, right? To have a perfect ground truth state for a real world system. There's always going to be some uncertainty because we're in the benchmark itself is going to have to do state estimation to figure that out. Like if you have objects, I mean, I guess you could put like nice, really good sensors within the object or do something else. But it's true that if that information is available for calculating the reward, then I guess someone could argue that information should be available to accomplish the task as well. So I don't know, I guess also I feel like that would increase the like complexity and cost of setting up the benchmark a lot. Having a noisy but monotonically correct metric that is a lot cheaper to implement could be worth if it helps scale up the system, the benchmarking system.
I don't know if this would be correct to say, but it seems to me that there are problems that is interesting from the perspective of robot learning. And also there are problems that are more application oriented. What I'm trying to say is that as a learning science person, you are really interested in, oh, what if I do this? Would it learn more efficiently? Should I use this state representation or that state representation, or like end-to-end versus like model-based? So these are all very interesting questions and moving the learning community forward. But also, I think we are in a transition stage that, like, I'm using it really in quotes, that like some, or let's say simplified problems that are used to move the learning community forward. I think that's coming to, like, there is transitioning to real applications as well. But that's not necessarily, the assumptions are different, right, in real applications. And I feel like we might be suffering from kind of a too focused of a perspective sometimes, when it comes to that. A quick example of that would be from robotic grasping literature, for example. For decades, people calculated grasping points on the objects. Like, should I put my finger exactly at this location, and then maybe exactly at this location, and then exactly at this location? Then would that be a stable grasp? What are the metrics that I should use? Like, that would give me a stable grasp, or how can I use these metrics to optimize the grasp, etc., etc. Then there were just couple work saying that, hey, these grasp metrics are actually irrelevant oftentimes to grasp success. That was one phenomenal work, I think. The other one is that people came up with soft hands and suction cups, and and like the paradigm has changed, right? So sometimes I think we are looking at too focused to our subdiscipline. For example, if I'm designing a hand, I'm just like looking at the hands, or or if it's the learning algorithm, just learning algorithm. But if we then start putting things together, I think then we started handling the real assumptions. Then it just,
So I'm actually curious, following up on that, if we designed some remote cloud benchmark with, okay, it's got this arm and this gripper and this task, how can we prevent narrowing our focus too much into this sort of environment? And then maybe we're missing out on hardware developments 5 years from now.
Yeah, I think that's a good question, especially like thinking of, parallel jaw grippers. We spend a lot of time using them, but they're really bad. Like they do tasks in really dumb ways compared to how, if in 2 or 3 years there's better fingered grippers that can do in-hand manipulation and solve a task in a much more like simple approach, then we're gonna be sad. So it seems like the advantage of having the benchmark be simply a task rather than a whole setup is that then there's also encouraging people to explore more on the hardware side as well as the algorithm side. But of course, then you can't do the nice remote cloud thing everyone logs into and uploads their model.
Yeah, I think also one issue with robotic clouds is the rapid technological advancements. So if you do a bunch of benchmarks and then you upgrade the system, how do you deal with the previous algorithms? Do you have to run them all again? What if they don't work? Right now you have a 3-fingered hand instead of a 2. Are they all thrown away? Do you need to resubmit them? So it's a real problem it's one issue with the idea of a remote cloud setup is suddenly there's one setup, everyone uses it, and as soon as you upgrade it, that data we're back to where we kind of started.
Just as a counterpoint, right? We need to, so I guess we have to make a choice of, are we trying to solve the entire problem, or are we trying to solve a piece of the problem, right? Are we trying to solve hardware? Are we trying to solve algorithms? Like, what are we actually trying to solve? Because if you're trying to solve the whole sort of problem in a holistic way, that is going to be a much harder thing to actually benchmark, because the range of options you have over there is just endless, right? And so I think in some sense we have to choose what is our benchmark trying to even do. Like, what is the goal of that specific benchmark, right?
I totally agree with that. Again, like if you are trying to understand whether this state representation or that state representation is better for learning faster this particular problem, then you need a very specific benchmark, right? But I think it was also in Anka's presentation too, like it was, so the way that she formulated the problem, like basically saying that, hey, what we need is controlled experiments. We need to understand primary things that are affecting our system. We also need to be very conscious about second order effects. If second order effects are taking over, then we should be presenting it that way in our papers. Yes, but that assumes a very incremental development process in robotics. Again, you are just changing one parameter, you are using all the algorithms as the same. But oftentimes, for example, if you are switching from a rigid gripper to soft gripper, your algorithm, you cannot keep your algorithm the same, or you wouldn't want to, not can't, you wouldn't want to keep your algorithm the same. There are algorithms that works better on this. Now you probably want a different perception module that works better with this algorithm. And like, you know, everything just affects everything. So in that way, unless we are working with like really looking into the science aspect of it, in the sense that whether this state representation, that state representation, or something very specific on robot learning or mechanism design or whatnot, I think that other than that, if we are looking into it in a task level, so what we try to do, actually, we try to make these into 3 categories, which was like mechanism benchmarking, algorithm benchmarking, and system level benchmarking. Then mechanism benchmarking, you can imagine. Algorithm benchmarking is more like looking into specific aspects of algorithms, when then you need a standardized systems perhaps. But when you are looking into more task level or system level benchmarking, then there should be a way to abstract it from the hardware that you are using. Give this task specifications, give the task constraints, give assumptions that people should take in order to solve this particular problem. Then you are free to go, because otherwise there will be a lot of backlash, you know, from this group, that group, from this approach, that approach, I guess.
So I might. The follow-up question there is, how do you actually implement that in a remote setup, right? So if I'm going to buy the robots, how do I enable you to have hardware freedom? Is it something like, well, you can come in and attach your new gripper to our center, or you mail it to us, or, you know, how would that actually work?
So one thing, UMass Lowell has a center called Nerve Center. In that Nerve Center, they have more than 10 robots, I guess. Again, more than 10 grippers, more than 10 whatever. Like from like each sensor that they know they bought. You know, 4 sensors, every single one that they know they bought. All robot arms and everything. So now there's the center that you can actually choose from and do those kind of control experiments. Basically, keep the algorithm the same, take the gripper. Yeah, that now becomes possible with that kind of setup. That is one option, I guess.
Yeah. So again, just going back to what I said earlier, right? We need to know what we're trying to benchmark. If you're trying to benchmark a system, then it becomes a lot harder, right? If you're trying to benchmark hardware, then you need a way to sort of control for the algorithmic aspects, right? And so we have to come to an agreement of what exactly are we trying to control for and what exactly are we trying to benchmark. So if you're benchmarking algorithms, then ideally you need to have a certain set of hardware and try to keep that stable for as long as we can. Now, even though we have seen a lot of hardware advancements, if you think about a manipulator, right, they've pretty much stayed the same for like, I don't know how many years, right? Even like using a 2-fingered end effector, you know, it's still been around for like so many years, right? So I think even though there's a lot of hardware advancements, there's a lot of time between when it actually is created and when it actually is being used by everyone. And so that sort of creates a natural control on the hardware itself.
This makes me think of how, like for like ImageNet competitions and stuff like that, every year there was a new challenge that was kind of in a similar vibe, but each year was a different set of images. I wonder if there could be some compromise between these two poles of having the remote benchmark and updating equipment. Is like every year you at the beginning of the year, you set what the hardware and the task is going to be for that year. Everyone has a chance to get set up on it, and then you evaluate or run on that one thing. And then next year, something might change and everyone gets the chance to update again. I mean, in theory, the hardware wouldn't be changing all the time, but it would kind of also prevent too much overfitting to any particular subtask or to a particular object. And it would kind of maybe keep the field moving.
Maybe indeed like this space of available robots or is not that big. I might agree your point in that sense, because there are rigid robots and there are more like compliant robots, for example, with Series S or whatever the mechanism to make it compliant. There's that. Indeed, like what's the difference between two rigid robots, right? I probably it doesn't make that much difference. Maybe from learning perspective it might, but if you are using the right abstraction levels, it should be fine, right? So maybe it's not that big, that space, because eventually we have end effectors, right? And manipulators, and that manipulator could be compliant or not. So yeah, maybe.
I think another thing to keep in mind is that the hallmark of a good benchmark is that making progress on that benchmark means that you're also making progress on in the field in general, right? And so a benchmark may become old, but the methods that were created by using those benchmarks will still live on, hopefully. Right. So the same thing we have seen with like ImageNet, for instance, is that okay, now there's like MS Coco, there's like so many other new and harder benchmarks to solve, but it does not mean that ImageNet is not being used or it's not as relevant in computer vision.
Does anyone have questions from the audience?
So I don't work in robot learning, but I'm coming from the formal methods side, and I specifically work on formal methods for testing and V&V for autonomous systems. So you can think of the DARPA challenge types of competitions where all these teams are required to design robots to meet a certain task, like a system level task requirement. And then the race officials kind of cleverly set up test environments to like challenge them. And so my work is more on, I guess, that side, like how do you come up with those interesting test environments automatically? I guess it's not so much of a question, but is there something like that we can do for robotics where, we focus on a single application. And if we also want to go one level deeper and kind of say, we want to benchmark algorithms, but we'll focus on self-driving as an application, then at the system level, I guess you can create like, Ducky Town like environments, like test environments. And within that, if you're focusing on benchmarking algorithms, maybe there's some specific tests that clearly demonstrate that, these algorithms for perception are better than these other ones or something like that. Just like trying to come from a different perspective and hear your thoughts on this.
Yeah, so I think the problem that I would see towards benchmarking at a system level like that is it's hard to pinpoint where the improvement is made, right? Is it the perception is better and thus you have a better state estimator that got you to where you are? Do you maybe have better motors, right? Did you get a Boston Dynamics? Did you develop that leg that suddenly your robot can do backflips, right? What was it? And sometimes that would be obvious, but what was it when you get to that system level to solve the task that actually improved, right? The benchmark goes up, but it's what did we improve? It's hard to indicate what part of the system made that improvement, because arguably you probably changed a lot of stuff. And so it's hard to pinpoint where that improvement was.
I on one hand completely agree. On the other hand, you can do an evaluation study up until a point, right? To a degree. But also, I think maybe it's fine. Maybe because so you are the person who, I mean, what we need is I believe a good discussion. For example, we wrote a paper. Yes, now I used a different hardware, which I think it gives advantages to me, and I'm now using maybe a algorithm that wouldn't be as successful with another hardware. Now it is successful with this hardware and beats the other system, or not. I don't know. So then we, as engineers, scientists, look at this, what has happened, and then just say, and let's just write it, right? This is like, let's write 1 page of discussion. if we have, like, this is what we think what has happened. And while writing that discussion, I think, I mean, we might add some couple experiments, again, like ablation study, that would say, hey, by removing this component, we showed like this much performance change in this and that. And it's fine. Some things are too complex to be, narrowing down to a granular level. And then, I believe if I explain, for example, this system, this algorithm is great, but really what made it work is my soft gripper, then you might, that's my take on it. And there can be your take on it. You might say no, and I will prove you wrong, and you might, right? So I think we don't have to quantify everything necessarily, which is a slippery slope, I know, but.
No, I think that's a good point. I guess my concern from the robotics side is just replicability, right? You can say that, but I can't take your system and put my algorithm on and be like, I know my algorithm did just as well. It's probably not your gripper, right? Or something like that. It's hard to, because robots are so complex, right? There's lots of moving parts and lots of little things you can change. Even if you just change low-level controllers or using different firmware, different kernels, something like that, you might get a different result. And so that's where I find it hard to say, it's not that I don't trust you, it's that, it's very hard to identify, and it's not as rigorous as it probably should be, right?
Any other questions from the audience? It's for Zoom.
So it's more of a general question. What I'm wondering is, do you feel, talking about the scalability and the generalization we need to take a step back from this rat race where we are promoting incremental progress by just publishing a lot of papers, and focus more on like coming up with general solutions by testing it on a wide range of algorithms, and also changing the dynamics, the hardwares, a lot of stuff on different environments. Do you think that would promote more progress, or this incremental progress is moving towards an overall progress?
So I kind of disagree, maybe, that we're not trying to do big progress. I think a lot of people are trying to do big progress, but it's luck. And if you try the right thing and it's big progress, that's great. But if it's not, and what you tried ended up being more incremental, then we should publish it so that other people know not to try the same thing again. And I'm sure there's definitely some situations where there's pressure to do incremental work. But on the other hand, I think it's hard to disentangle the existence of many incremental papers with like the attempt at doing less incremental work. If that makes sense.
So I think another way to also view it is in terms of the practicality of this whole thing. So let's say you start working on your idea to create like a big progress. And let's say you take like 5 years to do so, right? And in the meanwhile, someone else is also spending 5 years, but then only one of you has the right idea, right? And now if we move a little bit quicker, maybe when one person comes closer to a solution, everyone else can also work on that solution and make a faster progress, right? So in some sense, it's like a difference between an individual trying to make a big progress versus a community as a whole trying to make a big progress, right? So I think there's another perspective of that sort.
I can ask some more questions. Since you mentioned the making progress as a community, what do you all think the biggest hurdle is for uniting multiple institutions around a benchmark, especially across academia and industry? I guess this is a little shout out to Colleen here as our sort of industry representative. You've sort of established this DeepMind benchmark, but I'm not sure if we've seen as much adoption in academia, and why do you think that is?
Yeah, I mean, I think it's even without considering the industry versus academia, I think anytime someone makes a benchmark, it's difficult to get adoption. I mean, obviously like YCB was huge, and from then on, I think it's like it takes a lot of convincing, I think, to get people to change setups. But to get more collaboration with industry and academia, it's probably industry's job to provide resources, I think, in that sense. But I don't have a good good idea of that. I'm only a year and a half into my job here, so I'm not gonna make sweeping claims. I don't know if the academic side wants to comment.
So I think it's also about incentives, right? What is the incentive for, let's say, a lab to use the benchmark versus to not use the benchmark and just do their own thing in their lab, right? Now, if you go into any other field like NLP or like, computer vision, if you write a paper which has no result on a benchmark, it's looked down upon, right? Because you do not know if it actually works or not. If you just have your own benchmark that no one else uses. But we don't have the same thing in robotics, right? We just very accepting of works which just have their own objects, own environments, own everything. Right? So I think there's an incentive issue over here that if that is seen to be okay by the community, why should someone use the benchmark?
Yeah, I agree. We are very sweet to each other. Like I know I don't think we should turn into that, but like some maybe from my colleagues from other sciences, they literally like diss each other all the time, and especially like social sciences is all about that, right? So they basically just dissing each other continuously, basically, and they write papers like I don't know. Just one thing that comes to my mind is like forget Foucault. It's just like, and then Foucault writes something, it's just like forget this guy, and then like whatever. So we are always, I think, and in robotics, I don't remember seeing a paper saying that, hey, this algorithm, they say it works well, but it actually does not. I don't think that no one did that, and it's I think fine that we have a supporting community, and I don't advocate for like very harsh discussions or anything, but yeah, maybe I mean, a good way of doing this is a very comprehensive comparative study, right? And just like, hey, at least with my system, I implemented all these algorithms to the best of my knowledge. If you are, if you disagree, just tell me. But we don't have good mechanisms for that either, right? Like in other places there are, for example, short papers or rebuttal papers and like stuff like that. Yeah, I don't know. Again, it can get ugly very quickly, but
I think one of the issues is also robotics is still very young, right? We're still very much in the look what I can do phase, and we're starting to push out of that. And there are established methods that you can say, path planning is a big one, right? Been done to death, and people can start discussing about what's better and what's not. But for a lot of things, it's still, look, I got in the multi-robot demands, oh, look, we got 30 robots to actually do formation control in the real world, right? We're still at that phase of the problem where, it's, wow, you got it up there. I don't really care how it worked. Good job. So it's hard to start talking about benchmarking when you're still in that very young learning to walk phase and in a lot of disciplines, right? Some disciplines.
So also, I think there's a lot of inside knowledge in labs that are always inside the lab and never goes out, right? So for instance, like if I'm working on a paper, I've tried out so many different approaches, but I may not have to report all of those approaches, right? I may have also tried out the work of many other sort of labs, and the ones which I cannot make work well, sometimes I will not even show it in my paper because I'm not sure if I made a mistake in it or if the method is bad, right? And because if there's no open source code, I cannot say anything, right? Which is also an issue of like saying a negative result, because if there's no open source code, you cannot say it does not work because maybe I did not implement it properly.
I do think though that we do have some amount of like benchmarking that there, at least in robot learning, in simulation, which like, I don't know, like the Mojoko tasks or the D4RL offline RL code base benchmark. And it is really nice when I've used those because I can pull a number like out of a table and then stick it in a table in my paper, which is much less work than trying to re-implement or rerun someone else's code on my environment. And I know that's like a big advantage that people have in other fields where they have standard benchmarks, so they can take a number and put in a thing. But it's on simulation, so it's like, how relevant? What does it mean? It doesn't matter at all. And that's kind of an unfortunate situation.
No, so this is also an argument for having that remote access hardware piece, because then you have the code base, right? Along with the paper you publish, here's the literal code I ran. Maybe it's not commented well, whatever, but if you send it, it will do exactly, and you'll get the exact results. And then you can do direct comparison. So.
Yeah, I totally agree with both of these points. Yeah.
Okay, I think we'll wrap up our panel with that. So let's thank our panelists. So now we're moving into our roundtable discussions. So the way this is going to work is we're going to divide into two groups, and we're going to have sort of little mini thematic discussions. And so these are just for the in-person participants. I will share a slide that has some questions on it. But also, does anyone have any suggestions of roundtable topics that might be different from the ones I've picked? Okay, well, drum roll here. Let's see. There we go. So the two topics I had sort of divided is one is about sort of the role of benchmarks versus more creative experimental research. and how that might shape our field. And the other one is perhaps a little bit more tangible about what features we would want in a task or an environment in a robotics cloud. So maybe we can have the data set and environment features people over here and the benchmarking experimental people over here. The thinking is we'll discuss for maybe like 20 minutes and then we'll come back as a group and share our findings once we've solved all of these problems. Yeah, so you can pick whichever topic you'd like to discuss.
I guess the earlier you decide, the more